Welcome to our Solar System Full Guide, your comprehensive journey through the wonders of our cosmic neighborhood. In this series, we will explore each planet, delve into the mysteries of the Sun, and venture beyond to the outer edges of our solar system. The solar system is a vast and fascinating expanse, home to diverse celestial bodies, each with unique characteristics and secrets waiting to be uncovered. From the scorching surface of Mercury to the icy plains of Neptune, every corner holds stories that have shaped our understanding of the universe. Our journey begins at the center with the Sun, the star that provides the energy necessary for life on Earth and governs the motion of all planets and objects within its gravitational grasp. Understanding the Sun's complex processes and powerful phenomena is key to appreciating the dynamic nature of our solar system. We then move outward to Mercury, the closest planet to the Sun. Known for its swift orbit and extreme temperature variations, Mercury offers a glimpse into the challenges of proximity to a stellar giant. Its surface, marked by craters and ancient lava plains, tells a tale of a turbulent past. Next, we explore Venus, a planet shrouded in thick clouds and intense heat. Often called Earth's twin due to its similar size and composition, Venus presents a stark contrast with its hostile environment, dominated by volcanic activity and a runaway greenhouse effect. Our home planet, Earth, comes next. Unique in its ability to support life, Earth's complex systems of atmosphere, geology, and biosphere create a delicate balance that has allowed life to flourish. We will examine what makes Earth special and the ongoing challenges it faces. Mars, the red planet, has long been a focus of fascination and study. With its evidence of past water flow and potential for future human exploration, Mars stands as a beacon in our quest to find life beyond Earth and understand our place in the cosmos. Jupiter, the giant of our solar system, with its swirling clouds and massive storms, offers a window into the processes that govern gas giants. Its numerous moons, each a world of its own, add layers of intrigue and complexity to our exploration. Saturn, famous for its stunning ring system, invites us to ponder the forces that shape such magnificent structures. Beyond the rings, Saturn's diverse moons, like Triton and Enceladus, hold clues to the broader mysteries of planetary science. Uranus, with its unique tilt and icy atmosphere, challenges our understanding of planetary dynamics. This ice giant's moons and faint rings add further depth to our knowledge of the outer solar system. Finally, we reach Neptune, the farthest known planet, with its intense winds and dynamic atmosphere. Neptune's largest moon, Triton, with its retrograde orbit and icy geysers, promises insights into the distant reaches of our solar system and beyond. The Sun, a massive sphere of glowing plasma, is the heart of our solar system. Composed primarily of hydrogen and helium, it generates immense energy through nuclear fusion in its core. This fusion process converts hydrogen into helium, releasing energy that powers the Sun and illuminates our entire solar system. At the core, temperatures soar to about 15 million degrees Celsius. This intense heat and pressure create the perfect environment for nuclear fusion. The energy produced in the core slowly radiates outward, taking thousands of years to reach the Sun's surface. Surrounding the core is the radiative zone, where energy moves outward in the form of electromagnetic radiation. This layer is so dense that photons can take a long time to pass through it. Above the radiative zone lies the convective zone, where rising and falling currents of hot plasma transport energy to the surface. The Sun's surface, known as the photosphere, is the visible layer that emits the light we see. It's here that sunspots, cooler, darker regions caused by magnetic activity can be observed. The photosphere's temperature is around 5,500 degrees Celsius, significantly cooler than the core, but still incredibly hot. Beyond the photosphere is the chromosphere, a layer characterized by a reddish glow visible during solar eclipses. This region is dynamic, with spicules and flares bursting from the surface. The temperature in the chromosphere rises from about 4,000 to 20,000 degrees Celsius as you move outward. The outermost layer of the Sun's atmosphere is the corona, an extremely hot and tenuous region extending millions of kilometers into space. The corona's temperature can reach up to a few million degrees Celsius, and it's the source of the solar wind, a stream of charged particles that flow outward through the solar system. Sunspots and solar flares are among the most fascinating solar phenomena. Sunspots are caused by intense magnetic activity, which inhibits convection and results in cooler areas on the Sun's surface. Solar flares, on the other hand, are sudden eruptions of energy that can affect space weather and communications on Earth. The Sun's magnetic field is incredibly complex and dynamic. It drives the 11-year solar cycle, during which the number of sunspots increases to a maximum and then decreases to a minimum. This cycle influences solar activity and can have significant effects on the Earth's magnetosphere. Solar prominences are large, bright features extending outward from the Sun's surface. They are anchored to the photosphere and extend into the corona, forming looping structures that can last for weeks or even months. Prominences are associated with the Sun's magnetic field and are visible during solar eclipses or with specialized instruments. The solar wind, a continuous flow of charged particles from the Sun, shapes the heliosphere, the bubble-like region of space dominated by the solar magnetic field. The solar wind interacts with the Earth's magnetosphere, causing phenomena such as the auroras and geomagnetic storms. The Sun's influence extends far beyond the planets. Its gravitational pull holds the solar system together, and its energy drives the climates and weather patterns of planets. Understanding the Sun's structure and behavior helps us comprehend the environment in which our solar system exists. The study of the Sun, known as heliophysics, involves various observational techniques and missions. Spacecraft like the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe provide critical data about the Sun's structure, dynamics, and influence on the solar system. Solar research has practical implications for technology and society. Solar storms can disrupt satellite communications, power grids, and navigation systems. By studying the Sun, scientists can better predict space weather events and mitigate their impacts on Earth. The Sun will not remain constant forever. It's currently in the middle of its main sequence phase, where it has been for about 4.6 billion years. Eventually, it will exhaust its hydrogen fuel and evolve into a red giant, profoundly altering the solar system in the process. Understanding the Sun's life cycle and its future evolution is crucial for grasping the long-term dynamics of our solar system. This knowledge also provides insights into the life cycles of other stars in our galaxy. Our exploration of the Sun reveals the intricate balance of forces and processes that sustain it. This dynamic star continues to fascinate scientists and skywatchers alike, driving our quest to uncover the secrets of the cosmos. The Sun's energy production is a marvel of nuclear physics. Deep within its core, hydrogen nuclei undergo fusion to form helium, releasing an enormous amount of energy in the process. This energy is what powers the Sun and provides the light and heat essential for life on Earth. The process begins with the fusion of hydrogen atoms into deuterium, a rare form of hydrogen with one proton and one neutron. This step releases a positron and a neutrino, along with a significant amount of energy. Deuterium then fuses with another hydrogen nucleus to form helium-3, releasing even more energy. In the final step of the fusion process, two helium-3 nuclei collide to form helium-4, releasing two protons in the process. This series of reactions, known as the proton-proton chain, is the dominant source of energy production in the Sun. Each cycle converts four hydrogen nuclei into one helium nucleus and releases energy in the form of gamma rays. The gamma rays produced in the core take a long time to reach the surface. They are absorbed and re-emitted countless times by the dense solar material, gradually losing energy and shifting to lower energy photons, such as visible light. This journey through the radiative zone can take thousands of years. In the convective zone, energy is transported by the movement of hot plasma. Hot plasma rises to the surface, cools, and then sinks back down to be reheated. This convective motion helps to transport energy from the interior of the Sun to its outer layers, where it can finally be radiated into space. The balance of forces within the Sun is crucial for its stability. The outward pressure from the energy produced by nuclear fusion balances the inward pull of gravity. This equilibrium ensures that the Sun remains stable and does not collapse under its own weight or explode. The energy production process in the Sun is incredibly efficient. Even though the Sun loses mass due to the energy radiated away, it has enough fuel to continue shining for billions of years. This long-term stability has allowed life to develop and thrive on Earth. Neutrinos produced in the core escape the Sun almost immediately. These nearly massless particles travel at nearly the speed of light and pass through most matter without interaction. Detecting solar neutrinos provides a direct way to study the nuclear reactions occurring in the Sun's core. Solar observatories on Earth and in space measure the Sun's energy output across different wavelengths. These observations help scientists understand the various processes occurring within the Sun and monitor its activity. Variations in the Sun's energy output can influence the Earth's climate and space weather. Solar flares and coronal mass ejections are examples of sudden releases of energy from the Sun's surface. These events can release as much energy as billions of nuclear bombs and send charged particles streaming towards Earth, impacting satellite operations and power grids. The Sun's energy output has been remarkably stable over long periods, providing a consistent source of energy for the Earth. However, even small variations can have significant effects on our planet's climate. Understanding these variations is crucial for predicting future climate changes. Research into the Sun's energy production also informs our understanding of other stars. By studying the Sun, we gain insights into the processes that power stars throughout the universe. This knowledge helps astronomers understand the life cycles of stars and the evolution of galaxies. The study of the Sun's energy production is an interdisciplinary field involving astrophysics, nuclear physics, and plasma physics. Scientists use advanced computer models to simulate the Sun's internal processes and predict its future behavior. These models are continually refined with new observational data. Space missions like the Parker Solar Probe and the Solar and Heliospheric Observatory provide detailed measurements of the Sun's properties. These missions help to improve our understanding of the Sun's energy production and its impact on the solar system. The Sun's energy production is a testament to the power of nuclear fusion. Harnessing this process on Earth could provide a nearly limitless source of clean energy. Research into nuclear fusion technology is ongoing, inspired by the processes occurring in our very own star. Understanding the intricacies of the Sun's energy production not only deepens our knowledge of the cosmos, but also highlights the interconnectedness of all things in the universe. This journey into the heart of our star reveals the fundamental forces that shape our solar system and sustain life on Earth. Solar phenomena offer some of the most dramatic and dynamic sights in our solar system. Among these are sunspots, which appear as dark patches on the sun's surface. Sunspots are cooler regions caused by intense magnetic activity, inhibiting convection and resulting in reduced surface temperature. Sunspots typically appear in pairs or groups, aligning along the sun's magnetic field lines. These regions can be many times larger than Earth and persist for days to weeks. They serve as indicators of the sun's magnetic activity and are more numerous during the solar maximum phase of the solar cycle. Solar flares are another fascinating phenomenon. These are sudden bursts of radiation caused by the release of magnetic energy stored in the sun's atmosphere. Solar flares occur near sunspots and can release as much energy as billions of nuclear bombs in a matter of minutes. Flares emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. They can impact Earth's ionosphere, causing radio blackouts and affecting GPS and communication signals. The strongest flares are classified as X-class, with M-class and C-class being progressively weaker. Coronal mass ejections, or CMEs, are massive bursts of solar wind and magnetic fields rising above the solar corona and being released into space. Unlike flares, which are primarily bursts of electromagnetic radiation, CMEs involve significant amounts of solar plasma being ejected. When CMEs interact with Earth's magnetic field, they can cause geomagnetic storms. These storms can disrupt power grids, satellite operations, and communications systems. They also enhance auroras, creating spectacular light displays in the polar regions. Prominences are large, bright features that extend outward from the sun's surface. Anchored to the photosphere, they can reach thousands of kilometers into the corona. Prominences are composed of cooler plasma suspended in the hotter corona by magnetic forces. There are two main types of prominences: quiescent and active. Quiescent prominences form more slowly and can last for several months, while active prominences are shorter-lived and often erupt violently, sometimes leading to CMEs. The solar corona itself is a source of intrigue. Despite being much hotter than the surface, its faint glow is only visible during a total solar eclipse or with specialized instruments. The corona's temperature can reach millions of degrees, and it is the origin of the solar wind. Solar wind is a continuous stream of charged particles released from the corona. This wind varies in speed and intensity, influenced by the sun's magnetic activity. When it interacts with Earth's magnetosphere, it can create beautiful auroras and sometimes disrupt technological systems. The heliosphere is the bubble-like region of space dominated by the solar wind. It extends well beyond the orbit of Pluto, forming a protective shield against cosmic radiation. The boundary where the solar wind slows down and interacts with the interstellar medium is known as the heliopause. Understanding solar phenomena is crucial for space weather forecasting. Scientists use data from solar observatories and satellites to predict solar storms and mitigate their impact on Earth's technology and infrastructure. The study of solar phenomena also advances our knowledge of fundamental physical processes. Magnetic reconnection, plasma dynamics, and energy transfer in the sun's atmosphere are key areas of research, with implications for both astrophysics and practical applications on Earth. Solar cycles, typically lasting about 11 years, encompass periods of increased and decreased solar activity. Monitoring these cycles helps scientists understand long-term solar behavior and its potential effects on climate and space weather. Future missions aim to provide even more detailed observations of solar phenomena. Instruments like the Solar Orbiter and Parker Solar Probe offer unprecedented close-up views of the Sun, enhancing our understanding of these dynamic processes. Exploring solar phenomena not only reveals the complexities of our star, but also highlights the intricate connections between the Sun and Earth. This ongoing research continues to uncover the profound influence the Sun has on our planet and the broader solar system. The Sun's influence on the solar system is profound and far-reaching. Its gravitational pull keeps the planets, moons, asteroids, and comets in their orbits, ensuring the stability of our cosmic neighborhood. This gravitational dominance extends across the entire solar system, shaping the paths and behaviors of countless objects. The Sun's energy output drives the climates and weather patterns on planets with atmospheres. On Earth, the Sun's heat powers the water cycle, influences wind patterns, and sustains life through photosynthesis. The variation in solar radiation affects seasonal changes and climatic conditions. Solar radiation also plays a critical role in the chemical processes of planetary atmospheres. Ultraviolet light from the Sun causes the formation and destruction of ozone in Earth's stratosphere, protecting life by absorbing harmful UV radiation. On other planets, solar radiation drives atmospheric dynamics and chemical reactions. The solar wind, a continuous stream of charged particles emitted by the Sun, interacts with planetary magnetospheres and atmospheres. This interaction shapes the magnetospheres, creating phenomena such as the auroras on Earth and Jupiter. The solar wind can strip away atmospheric particles, as seen on Mars, which lacks a strong magnetic field. The heliosphere, the vast bubble of space influenced by the solar wind, acts as a shield against cosmic radiation. This protective barrier extends far beyond the orbit of Pluto, helping to reduce the influx of high-energy particles from interstellar space. The boundary of the heliosphere, the heliopause, marks the edge of the Sun's influence. Solar activity, including sunspots, flares, and coronal mass ejections, significantly impacts space weather. These activities can enhance the solar wind and produce geomagnetic storms, which affect satellite operations, power grids, and communications systems on Earth. Understanding solar activity is essential for predicting and mitigating these effects. The Sun's ultraviolet and X-ray radiation influences the ionospheres of planets. On Earth, changes in solar radiation levels can alter the density and composition of the ionosphere, affecting radio signal propagation and GPS accuracy. Other planets with ionospheres experience similar impacts. The Sun's light and heat are vital for life on Earth. Photosynthesis, the process by which plants convert sunlight into chemical energy, forms the base of the food chain. Solar energy also drives the productivity of ecosystems, influencing the distribution and behavior of organisms. The stability of the Sun's energy output over billions of years has allowed life to evolve and thrive on Earth. Small variations in solar radiation, such as those caused by the 11-year solar cycle, can influence Earth's climate. Long-term changes in the Sun's output have been linked to historical climate events. The Sun's influence extends to the outer solar system, affecting the environments of distant planets and their moons. For example, solar radiation drives the sublimation of ices on comets, creating their distinctive tails. Even at great distances, the Sun's energy affects the thermal and chemical properties of objects in the Kuiper Belt. In the asteroid belt, the Sun's heat causes the Yarkovsky effect, a force acting on rotating bodies due to uneven thermal radiation. This effect can alter the orbits of asteroids over long periods, potentially bringing some into collision courses with planets, including Earth. The Sun's gravitational influence also plays a role in the dynamics of the Oort cloud, a distant region of icy bodies surrounding the solar system. Disturbances in the Oort cloud can send comets into the inner solar system, influenced by the Sun's gravity. The Sun's impact on the solar system is not limited to its physical and energetic effects. It also serves as a fundamental reference point for timekeeping and navigation. The positions of the planets and their motions relative to the Sun are used to define calendars and guide space missions. The study of the Sun's influence on the solar system enhances our understanding of similar processes in other star systems. By observing how our Sun interacts with its planets, we gain insights into the behavior of exoplanetary systems, informing the search for habitable worlds. Exploring the Sun's influence helps us appreciate the interconnectedness of the solar system. The ongoing research into solar phenomena and their effects underscores the importance of the Sun in shaping the environment and conditions of our cosmic home. Solar cycles are approximately 11-year periods during which the Sun's activity waxes and wanes. These cycles are characterized by variations in the number and size of sunspots on the Sun's surface, reflecting changes in its magnetic activity. Understanding these cycles is crucial for predicting solar behavior and its impacts on the solar system. The cycle begins with a solar minimum, a period of low sunspot activity. During this phase, the Sun's magnetic field is weak and stable. Solar flares and coronal mass ejections are infrequent, and the Sun appears relatively calm. As the cycle progresses, sunspot numbers increase, leading to the solar maximum. This period of heightened activity sees more frequent and intense solar flares and coronal mass ejections. The Sun's magnetic field becomes more complex and dynamic, contributing to these energetic events. The solar maximum affects space weather significantly. Increased solar activity can enhance the solar wind and lead to geomagnetic storms. These storms can disrupt satellite operations, power grids, and communication systems on Earth. Predicting solar maximum conditions helps mitigate these effects. Auroras, or northern and southern lights, become more vivid and widespread during solar maximum. The increased solar wind interacts with Earth's magnetosphere, causing charged particles to excite atmospheric gases, producing stunning light displays. These natural phenomena are closely linked to the solar cycle's peak. During the solar cycle, the Sun's magnetic field undergoes a complete flip. This reversal occurs at the solar maximum, where the magnetic poles switch places. The process, known as solar magnetic polarity reversal, marks a critical point in the cycle and influences solar phenomena. Solar cycles also impact Earth's ionosphere. Increased ultraviolet and X-ray radiation during the solar maximum enhances ionization in the upper atmosphere. This can affect radio communications and GPS accuracy, necessitating adjustments for technological systems reliant on these signals. The solar cycle influences climate patterns on Earth. Though the effect is subtle compared to other climatic factors, variations in solar radiation can contribute to temperature fluctuations. Historical records show correlations between solar minima and cooler periods, such as the Maunder Minimum and the Little Ice Age. Satellite missions are designed with the solar cycle in mind. Engineers account for increased radiation and particle flux during solar maximum to protect sensitive equipment. Understanding the cycle helps in planning the timing and operation of space missions to ensure their longevity and success. Solar cycles also affect space exploration beyond Earth's orbit. Increased solar activity poses risks to astronauts due to higher radiation levels. Missions to the Moon, Mars, and other destinations must consider the solar cycle to ensure the safety of crew members. The study of past solar cycles provides insights into future solar behavior. By analyzing historical sunspot records and other solar data, scientists develop models to predict upcoming cycles. Accurate predictions are vital for preparing for potential impacts on technology and infrastructure. Solar activity influences the heliosphere, the bubble-like region dominated by the solar wind. During the solar maximum, the heliosphere expands due to increased solar wind pressure. This affects the boundary where the solar wind meets the interstellar medium, known as the heliopause. Solar cycles contribute to the variability of cosmic ray flux reaching Earth. During solar maximum, the strengthened solar wind and magnetic field reduce the influx of high-energy cosmic rays. Conversely, during solar minimum, the weakened solar wind allows more cosmic rays to penetrate the inner solar system. Understanding solar cycles is essential for advancing our knowledge of stellar dynamics. The Sun serves as a model for studying magnetic activity in other stars. By examining our solar cycles, astronomers gain insights into the magnetic behavior and activity cycles of distant stars, enhancing our comprehension of stellar evolution. The interplay between solar cycles and technological advancements underscores the importance of continued research. Monitoring the Sun's activity and refining predictive models ensure that society can better prepare for and adapt to the challenges posed by solar variability. The ongoing study of solar cycles reveals the dynamic nature of our star. These cycles, with their far-reaching effects, highlight the interconnectedness of solar activity and its influence throughout the solar system, underscoring the importance of understanding and predicting solar behavior. The physical characteristics of the Sun are defined by its vast size and powerful energy output. As a G-type main-sequence star, or G-dwarf, the Sun is composed primarily of hydrogen and helium, undergoing nuclear fusion at its core. This fusion process releases the energy that makes the Sun shine. The Sun's diameter is about 1.39 million kilometers, making it over 100 times wider than Earth. Its volume is so immense that it could contain approximately 1.3 million Earths. Despite its massive size, the Sun is considered an average star in terms of mass and diameter. At the core of the Sun, temperatures reach around 15 million degrees Celsius. This extreme heat and pressure are necessary for nuclear fusion, where hydrogen atoms combine to form helium, releasing enormous amounts of energy in the form of light and heat. Surrounding the core is the radiative zone, where energy moves outward as electromagnetic radiation. This layer extends from the core to about 70% of the Sun's radius. The temperature here ranges from 7 million degrees Celsius near the core to about 2 million degrees at the outer edge of the radiative zone. Above the radiative zone lies the convective zone, where energy is transported by the movement of hot plasma. In this region, temperatures drop from 2 million degrees to about 5,500 degrees Celsius at the surface. The convective currents create the granulated appearance of the Sun's photosphere. The photosphere is the Sun's visible surface layer, emitting the light we see. It has a temperature of approximately 5,500 degrees Celsius. The photosphere is where sunspots appear, indicating areas of intense magnetic activity that are cooler than the surrounding regions. Above the photosphere is the chromosphere, a layer characterized by a reddish glow visible during solar eclipses. The chromosphere's temperature ranges from about 4,000 to 20,000 degrees Celsius. This layer is dynamic, with spicules and solar flares erupting from its surface. The outermost layer of the Sun's atmosphere is the corona. Despite being much hotter than the photosphere, with temperatures reaching up to several million degrees Celsius, the corona is much less dense. Its faint glow can be seen during total solar eclipses or with specialized instruments. The Sun's magnetic field is a key physical characteristic, driving much of its dynamic activity. The magnetic field lines twist and tangle due to the differential rotation of the Sun, where the equator rotates faster than the poles. This twisting leads to the formation of sunspots, solar flares, and coronal mass ejections. Sunspots are temporary phenomena on the photosphere, appearing as dark spots due to their lower temperature. They can vary in size and can last from a few days to several months. Sunspots are often associated with solar flares and other magnetic activity. Solar flares are sudden eruptions of energy caused by the release of magnetic energy stored in the Sun's atmosphere. They emit radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays, impacting space weather and communication systems on Earth. Coronal mass ejections, CMEs, are large expulsions of plasma and magnetic field from the Sun's corona. When directed towards Earth, CMEs can cause geomagnetic storms, affecting satellites, power grids, and auroras. These events are closely monitored to mitigate their impacts on modern technology. The solar wind, a continuous flow of charged particles from the corona, extends the Sun's influence far beyond the planets. This wind shapes the heliosphere, a protective bubble around the solar system, and interacts with planetary magnetospheres, causing phenomena such as auroras. The Sun's rotation period varies with latitude. At the equator, it completes a rotation in about 25 days, while at the poles, it takes about 35 days. This differential rotation plays a crucial role in the Sun's magnetic activity cycle and the formation of sunspots and solar phenomena. Understanding the physical characteristics of the Sun provides insight into the fundamental processes that govern its behavior and influence the entire solar system. These characteristics shape the environment in which planets and other celestial bodies exist, emphasizing the Sun's central role in our cosmic neighborhood. The orbit and rotation of the Sun are fundamental to the dynamics of the solar system. While the Sun itself doesn't orbit around another star, it does move through the Milky Way galaxy. This movement is part of a complex journey that affects the gravitational relationships within the solar system. The Sun orbits the center of the Milky Way galaxy, taking approximately 225 to 250 million years to complete one revolution. This path is not a perfect circle, but an elliptical orbit, influenced by the gravitational pull of other stars and the galaxy's massive central black hole. The solar system orbits the galactic center at an average speed of about 828,000 kilometers per hour. This immense speed is necessary to counterbalance the gravitational pull of the galaxy, keeping the Sun and its orbiting planets in a stable path within the Milky Way. Within the solar system, the Sun's gravity governs the orbits of planets, moons, and other celestial bodies. The planets follow elliptical orbits, with the Sun situated at one of the two foci of each ellipse. This arrangement is a result of the laws of planetary motion described by Johannes Kepler. The Sun itself rotates on its axis, but unlike a solid body, its rotation is differential. This means that different parts of the Sun rotate at different speeds. The equatorial regions complete a rotation in about 25 days, while the polar regions take about 35 days. This differential rotation plays a critical role in the Sun's magnetic activity. As the Sun rotates, its magnetic field lines become twisted and tangled. This tangling can lead to the formation of sunspots, solar flares, and other magnetic phenomena driving the solar cycle. The rotational axis of the Sun is tilted about 7.25 degrees relative to the plane of the Earth's orbit. This tilt is much smaller than that of many planets, resulting in relatively stable solar activity levels over the course of the year compared to the seasonal variations experienced on Earth. The rotation of the Sun also affects the solar wind, a stream of charged particles flowing outward from the corona. The solar wind carries the Sun's magnetic field into space, creating a spiral pattern known as the Parker spiral. This pattern shapes the heliosphere and influences space weather. The interplay between the Sun's rotation and its magnetic field leads to a variety of solar phenomena. The 11-year solar cycle, marked by periodic increases and decreases in sunspot numbers, is driven by the complex dynamics of solar rotation and magnetic field interactions. Solar rotation is studied through techniques such as helioseismology, which analyzes sound waves traveling through the Sun. These studies reveal the internal structure and dynamics of the Sun, providing insights into its rotational behavior and the mechanisms driving solar activity. The Sun's rotation also has implications for the evolution of the solar system. Over time, the Sun's rotation has slowed due to the loss of angular momentum through the solar wind. This gradual deceleration affects the long-term dynamics of the Sun and its interaction with the surrounding space environment. The rotation period of the Sun can influence space missions. Understanding the Sun's rotational dynamics helps scientists predict solar activity and plan missions accordingly, ensuring the safety and success of spacecraft and astronauts. The Sun's orbit around the galactic center and its own rotation are interlinked with the gravitational forces of the entire solar system. These movements contribute to the stability of planetary orbits and the overall structure of our cosmic neighborhood. By studying the orbit and rotation of the Sun, astronomers gain insights into the fundamental forces that govern stellar and planetary dynamics. These insights help to understand not only our solar system, but also the behavior of other star systems in the galaxy. The continuous observation and analysis of the Sun's orbit and rotation reveal the intricate balance of forces at play in our solar system. This knowledge underscores the importance of the Sun's role in maintaining the harmony and stability of the cosmic environment we inhabit. The surface features and geology of the Sun are dominated by its dynamic and ever-changing nature. The photosphere, the Sun's visible surface, is a region marked by constant activity and various phenomena driven by magnetic forces. One of the most prominent features on the Sun's surface is granulation. Granules are small convective cells that transport heat from the interior to the surface. Each granule is about 1,000 kilometers across, and their patterns shift constantly, resembling boiling water. Sunspots are another key feature. These dark, cooler areas are caused by intense magnetic activity, which inhibits convection. Sunspots can vary greatly in size and can be larger than Earth. They often appear in groups and follow an 11-year cycle, increasing in number during solar maximum. The penumbra and umbra are parts of sunspots. The umbra is the darkest, coolest central region, while the penumbra surrounds it with a lighter, slightly warmer area. These features indicate the complex magnetic field structures within sunspots. Solar prominences are large, bright loops of plasma extending from the photosphere into the corona. These structures are anchored in the Sun's surface by magnetic forces and can last for days or months. Prominences can sometimes erupt, leading to coronal mass ejections. Plages and faculae are bright areas associated with magnetic activity. Plages are found in the chromosphere and appear brighter than the surrounding areas. Faculae are bright spots in the photosphere that become more prominent near the solar limb. Both features are linked to sunspot activity. Flares are sudden, intense bursts of energy caused by magnetic reconnection in the Sun's atmosphere. These explosive events release radiation across the electromagnetic spectrum and can significantly impact space weather, affecting satellite operations and communications on Earth. The chromosphere, just above the photosphere, is characterized by spicules. These are short-lived, jet-like eruptions of plasma that shoot up from the chromosphere. Spicules can reach heights of several thousand kilometers and contribute to the heating of the corona. The corona itself is an area of interest due to its high temperatures, which can reach millions of degrees Celsius. Coronal loops, formed by magnetic field lines filled with hot plasma, are common in active regions. These loops can be observed during solar eclipses or with specialized instruments. Coronal holes are regions where the sun's magnetic field opens into space, allowing high-speed solar wind to escape. These holes appear darker in X-ray and ultraviolet images and can influence space weather by contributing to geomagnetic storms when their solar wind reaches Earth. The heliosphere, influenced by the solar wind, extends far beyond the sun's surface. The interaction of the solar wind with interstellar space defines the boundaries of the heliosphere. The heliopause marks the outer edge, where the solar wind pressure balances with the interstellar medium. Understanding the surface features and geology of the Sun involves studying its magnetic field. The magnetic field lines emerge from the solar surface and can become twisted and entangled, leading to various solar phenomena like sunspots, flares, and prominences. Magnetic reconnection is a key process in solar geology. This occurs when oppositely directed magnetic field lines break and reconnect, releasing massive amounts of energy. This process is responsible for solar flares and contributes to the heating of the corona. Helioseismology is a method used to study the Sun's interior by observing oscillations on its surface. These oscillations provide insights into the Sun's internal structure and dynamics, revealing information about its composition, rotation, and magnetic fields. By continuously observing the Sun's surface features and geological activity, scientists gain valuable knowledge about the fundamental processes that drive the behavior of our star. This research not only enhances our understanding of the Sun, but also helps to predict and mitigate the impacts of solar activity on Earth and beyond. Mercury's magnetic field is one of the most intriguing aspects of this small planet. Unlike most other terrestrial planets, Mercury possesses a global magnetic field, albeit much weaker than Earth's. This field is generated by a dynamo effect in Mercury's partially molten outer core. The magnetic field of Mercury is about 1% the strength of Earth's magnetic field. Despite its weakness, it is strong enough to deflect the solar wind and create a magnetosphere around the planet. This magnetosphere is highly dynamic, constantly changing due to the influence of the solar wind. Mercury's magnetosphere has a distinctive structure. The interaction with the solar wind creates a bow shock on the sunward side, where the solar wind slows down abruptly. Beyond the bow shock lies the magnetosheath, a turbulent region where solar wind particles are heated and deflected. The magnetopause is the boundary separating Mercury's magnetosphere from the solar wind. Inside this boundary, the magnetic field dominates and controls the motion of charged particles. The magnetotail extends away from the Sun, similar to Earth's magnetotail, but is much more compressed. One of the most fascinating features of Mercury's magnetic field is its offset. The field is not centered at the planet's core, but is shifted towards the North Pole by about 20% of the planet's radius. This northward offset affects the distribution and behavior of charged particles within the magnetosphere. The offset magnetic field results in an asymmetrical magnetosphere. The northern hemisphere experiences stronger magnetic field interactions, while the southern hemisphere is more exposed to direct solar wind. This asymmetry has significant implications for the planet's space weather environment. Mercury's magnetic field creates magnetic poles near the geographic poles, but due to the offset, the northern magnetic pole is closer to the surface. This creates unique patterns of charged particle precipitation, influencing the surface and possibly contributing to the formation of Mercury's tenuous exosphere. The interaction between Mercury's magnetic field and the solar wind generates magnetic reconnection events. These events occur when magnetic field lines break and reconnect, releasing energy and accelerating particles. Mercury experiences frequent and intense reconnection due to its proximity to the Sun. Magnetic reconnection at Mercury leads to the formation of flux transfer events, which are bursts of magnetic energy transferred from the solar wind into the magnetosphere. These events are more frequent at Mercury than at Earth, reflecting the planet's closer and more direct exposure to the Sun. Mercury's magnetosphere traps energetic particles, creating radiation belts similar to those around Earth. However, Mercury's radiation belts are much weaker and more variable due to the planet's smaller size and weaker magnetic field. These belts are influenced by solar activity and magnetic reconnection. The Messenger spacecraft provided valuable data on Mercury's magnetic field during its mission. It mapped the magnetic field in detail, revealing its structure, strength, and dynamics. Messenger's observations have significantly advanced our understanding of Mercury's magnetic environment. The weak but significant magnetic field of Mercury raises questions about the planet's interior. The dynamo effect suggests that Mercury's core remains partially molten, despite the planet's small size and proximity to the Sun. This finding has implications for our understanding of planetary formation and thermal evolution. Studying Mercury's magnetic field helps scientists compare magnetic dynamos in different planetary bodies. The differences and similarities between Mercury's and Earth's magnetic fields provide insights into the fundamental processes driving magnetic field generation in rocky planets. Mercury's magnetic field also influences the planet's surface geology. The interaction between the magnetic field and solar wind particles contributes to space weathering, which alters the chemical and physical properties of the surface. This process affects the reflectance and composition of Mercury's regolith. Understanding Mercury's magnetic field is crucial for future missions to the planet. The dynamic magnetosphere poses challenges for spacecraft operations and communications. Knowledge of the magnetic environment helps in planning safe and effective exploration strategies for Mercury and similar planetary bodies. Exploration missions to Mercury have provided invaluable insights into this enigmatic planet. The first spacecraft to visit Mercury was Mariner 10, launched by NASA in 1973. Mariner 10 conducted 3 flybys of Mercury, capturing the first close-up images of the planet's surface. Mariner 10 revealed a heavily cratered landscape similar in appearance to the Moon. It also discovered Mercury's weak magnetic field, a surprising find given the planet's small size. These initial discoveries laid the groundwork for future exploration and study. Decades later, NASA's Messenger mission was launched in 2004. Messenger, short for Mercury Surface, Space Environment, Geochemistry and Ranging, was designed to orbit Mercury and provide comprehensive data about the planet. It entered orbit around Mercury in 2011. Messenger's primary objectives included mapping Mercury's surface, studying its magnetic field, and analyzing its composition. Over its 4-year mission, Messenger collected detailed images and data, significantly enhancing our understanding of Mercury's geology and environment. One of Messenger's key discoveries was the presence of water ice in permanently shadowed craters near Mercury's poles. Despite the planet's extreme temperatures, these regions remained cold enough to preserve ice, offering clues about water delivery in the inner solar system. Messenger also confirmed the existence of volatile elements like potassium and sulfur on Mercury's surface. These findings challenge previous assumptions about the planet's formation and suggest that Mercury retained more volatile materials than previously thought. The spacecraft provided detailed maps of Mercury's surface, revealing a complex history of volcanic and tectonic activity. Messenger identified large volcanic plains and evidence of tectonic forces that shaped the planet's surface over billions of years. One of the most intriguing findings was the discovery of hollows, unique depressions with bright reflective material. These hollows appear to be relatively young features, formed by the sublimation of volatile substances from Mercury's crust and are not found on any other planet. Messenger's data on Mercury's magnetic field showed it to be both weak and offset. This offset magnetic field provided clues about the planet's internal structure and the dynamo process generating the magnetic field. These findings have implications for understanding the dynamics of planetary cores. In 2018, the European Space Agency and Japan Aerospace Exploration Agency launched the BepiColombo mission to Mercury. BepiColombo consists of two orbiters, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter. The mission aims to build on Messenger's discoveries. BepiColombo will provide detailed measurements of Mercury's magnetic field, magnetosphere, and interior structure. It will also map the surface with high-resolution cameras and analyze the planet's exosphere, enhancing our understanding of Mercury's environment. The mission will offer new insights into Mercury's polar regions and the distribution of water ice. BepiColombo's advanced instruments will help unravel the mysteries of the planet's geological history and the processes that shaped its surface. Exploration missions to Mercury face significant challenges, including extreme temperatures and intense solar radiation. These missions require innovative engineering solutions to protect instruments and ensure successful data collection in such a harsh environment. Future missions to Mercury may focus on landing on the planet's surface, providing direct analysis of its geology and composition. Such missions could offer unprecedented insights into the planet's history and the broader processes of planetary formation in the inner solar system. The discoveries made by Mariner 10, Messenger, and BepiColombo underscore the importance of continued exploration. Each mission builds on the knowledge gained from previous ones, revealing the complexities of Mercury and its role in our solar system's history. By exploring Mercury, scientists gain a deeper understanding of the processes that govern rocky planets. These missions not only enhance our knowledge of Mercury, but also provide comparative data for studying other terrestrial planets, including Earth, Venus, and Mars. Mercury's atmosphere is incredibly thin, often referred to as an exosphere rather than a true atmosphere. It is composed mainly of oxygen, sodium, hydrogen, helium, and potassium. This thin layer of gases is constantly replenished by solar wind, micrometeoroid impacts, and the planet's surface materials. The exosphere of Mercury is not stable and varies greatly with time and location. Solar radiation pressure and the planet's magnetic field influence its dynamics. These variations make Mercury's exosphere a subject of intense study, as it offers clues about surface and solar interactions. Due to its proximity to the Sun, Mercury experiences extreme temperature variations. Daytime temperatures can soar up to 430 degrees Celsius, while nighttime temperatures can plummet to minus 180 degrees Celsius. This dramatic temperature range is one of the most significant in the solar system. Mercury's slow rotation contributes to these extreme temperature differences. It takes about 59 Earth days for Mercury to complete one rotation, meaning its day and night cycles are long. This slow rotation allows the planet's surface to heat up and cool down dramatically. The absence of a significant atmosphere means there is no medium to distribute heat around the planet. As a result, the side facing the sun becomes extremely hot, while the side facing away becomes extremely cold. This lack of atmospheric insulation starkly contrasts with planets that have thicker atmospheres. Mercury's surface pressure is almost negligible, about 1 trillion times less than Earth's atmospheric pressure at sea level. This lack of pressure is due to the thin exosphere, which cannot retain heat or distribute it across the planet's surface, contributing to the temperature extremes. Solar radiation and micrometeoroid impacts continually strip away particles from Mercury's exosphere, creating a constantly changing environment. This process of particle ejection and replacement leads to a dynamic and transient exosphere, unlike the more stable atmospheres of larger planets. Mercury's proximity to the Sun also subjects it to intense solar radiation. This radiation breaks down surface materials, releasing atoms and molecules into the exosphere. The process, known as photon-stimulated desorption, is a key mechanism maintaining the planet's thin atmosphere. Magnetic storms on the Sun can significantly impact Mercury's exosphere. During solar storms, enhanced solar wind interacts with the planet's magnetic field, leading to increased particle ejection from the surface. These interactions cause temporary spikes in the density and composition of the exosphere. The study of Mercury's exosphere provides insights into surface processes and solar interactions. By analyzing the composition and behavior of the exosphere, scientists can infer the types of materials present on Mercury's surface and the nature of their interactions with solar radiation. Mercury's surface shows evidence of long-term climate processes, despite the lack of a substantial atmosphere. Features such as hollows and scarps suggest a history of volatile element loss and tectonic activity. These geological features are linked to the planet's thermal evolution and surface changes over time. The presence of water ice in permanently shadowed craters at Mercury's poles is a surprising discovery. Despite the planet's high daytime temperatures, these shadowed regions remain cold enough to preserve ice. The ice likely originates from cometary impacts or volcanic outgassing. The distribution of ice and volatile materials on Mercury is influenced by the planet's tilt and rotation. Mercury's axial tilt is minimal, meaning the poles receive very little sunlight, creating cold traps where ice can accumulate and persist. Understanding the atmosphere and climate of Mercury helps scientists compare it with other terrestrial planets. Mercury's extreme environment provides a natural laboratory for studying planetary formation, surface interactions with solar wind, and the effects of proximity to a star. Exploring Mercury's atmosphere and climate challenges our understanding of planetary science. The insights gained from this small, extreme planet enhance our knowledge of the fundamental processes shaping planetary atmospheres and climates throughout the solar system. Mercury's surface is a landscape of contrasts, shaped by a combination of impact cratering, volcanic activity, and tectonic forces. The planet's proximity to the Sun and lack of a significant atmosphere have left its surface exposed to intense solar radiation and micrometeoroid bombardment. Impact craters dominate Mercury's surface, ranging from small, simple craters to large, complex basins. The largest impact feature is the Colorus Basin, measuring about 1,550 kilometers in diameter. This massive impact structure is surrounded by concentric rings and extensive plains formed by the shock waves of the impact. The surface also features smooth plains, which are vast, relatively flat regions formed by volcanic activity. These plains are found both inside large basins and between craters, suggesting widespread volcanic resurfacing events in Mercury's past. The smooth plains are younger than the heavily cratered terrains, indicating that volcanic activity played a significant role in shaping the planet's surface. Volcanic vents and lava flows provide evidence of Mercury's volcanic history. These features suggest that the planet experienced prolonged periods of volcanic activity. The presence of pyroclastic deposits formed by explosive volcanic eruptions indicates that volatile substances were involved in Mercury's volcanism. Hollows are one of the most intriguing surface features on Mercury. These bright, shallow depressions appear to be unique to the planet. Hollows are thought to form through the loss of volatile materials, which sublimate and leave behind these distinct features. Their bright appearance suggests they are relatively young and still actively forming. Scarps or cliffs crisscross Mercury's surface, indicating tectonic activity. These scarps are the result of the planet's interior cooling and contracting over time. As Mercury's core cooled, the surface crust shrank and cracked, creating these steep cliffs. Lobate scarps can extend for hundreds of kilometers and reach heights of up to 3 kilometers. The planet's surface also shows signs of ancient lava plains, which suggest that Mercury's interior was once hot enough to produce extensive volcanic activity. These plains are similar to the Lunar Maria and indicate that volcanism was an important process in Mercury's geological history. Intercrater plains, found between large impact craters, are some of the oldest surfaces on Mercury. These plains are heavily cratered and have been shaped by both impact events and volcanic resurfacing. Their ancient nature provides a window into the early history of the planet. Mercury's volcanic activity has left a lasting impact on its surface composition. Spectral analyses from spacecraft reveal that the planet's crust is rich in magnesium and sulfur, which are indicative of volcanic processes. These elements suggest that Mercury's volcanism involved materials from the deep interior, brought to the surface by volcanic eruptions. Volcanic vents on Mercury come in various forms, including simple pits and complex calderas. Some vents are surrounded by bright, reflective halos, indicating the presence of volatile, rich materials. These vents provide crucial clues about the composition of Mercury's interior and the nature of its volcanic activity. The planet's surface also features ridges and troughs formed by tectonic forces. These structures indicate that Mercury's crust has been shaped by compressive and extensional stresses. The ridges and troughs are often associated with impact basins, suggesting that the planet's tectonic activity is influenced by its impact history. Mercury's highlands are heavily cratered regions that represent some of the oldest surfaces on the planet. These highlands are interspersed with younger volcanic plains, indicating a complex geological history involving both impact cratering and volcanic resurfacing. The surface of Mercury is covered with a layer of regolith, a mix of dust, soil, and broken rock. This regolith is formed by the constant bombardment of micrometeoroids and larger impactors. The regolith's composition reflects the diverse geological processes that have shaped the planet's surface. Studying Mercury's surface and volcanic activity provides insights into the planet's geological evolution. By analyzing surface features and volcanic deposits, scientists can reconstruct the history of Mercury's interior processes and understand how the planet has changed over billions of years. Mercury's geological features offer a unique perspective on planetary formation and evolution. The combination of impact cratering, volcanic activity, and tectonic forces has created a rich and varied landscape. Understanding these processes on Mercury helps scientists draw comparisons with other terrestrial planets, enhancing our knowledge of the solar system's history. Venus has a unique orbit and rotation that sets it apart from other planets in the solar system. It orbits the Sun at an average distance of about 108 million kilometers, making it the second planet from the Sun. Venus's orbit is nearly circular, with an eccentricity of less than 0.01, meaning it follows a very stable path around the Sun. One of the most striking features of Venus's orbit is its length. It takes approximately 225 Earth days for Venus to complete one orbit around the Sun. This is known as a Venusian year. In comparison, Earth takes 365 days to complete its orbit, highlighting the differences in orbital periods between the two planets. Venus's rotation is even more unusual. It rotates on its axis very slowly, taking about 243 Earth days to complete one rotation. This means that a day on Venus, known as a sidereal day, is longer than a Venusian year. This slow rotation rate is the slowest of any planet in the solar system. Adding to the peculiarity, Venus rotates in the opposite direction to most planets in the solar system. This retrograde rotation means that if you were standing on Venus, you would see the Sun rise in the west and set in the east, contrary to the experience on Earth. The reason for Venus's retrograde rotation is not entirely understood, but it is believed to be the result of a significant collision with another large celestial body early in the planet's history. This impact could have altered Venus's rotational direction and slowed its rotation significantly. The slow and retrograde rotation of Venus affects its atmosphere and weather patterns. The planet's thick atmosphere, composed mainly of carbon dioxide, rotates much faster than its surface, creating a superrotational wind that circulates the entire planet in just a few Earth days. Venus's axial tilt is minimal, only about 3 degrees. This small tilt means that Venus does not experience significant seasonal changes like Earth. The uniformity of the planet's tilt contributes to the extreme and consistent temperatures across its surface. The combination of a long rotational period and minimal axial tilt results in a very stable climate, with little variation between day and night temperatures. However, the thick atmosphere and intense greenhouse effect cause surface temperatures to remain consistently high, averaging around 467 degrees Celsius. The dense atmosphere and cloud cover of Venus also play a role in its heat distribution. The thick clouds reflect much of the incoming solar radiation, while the greenhouse gases trap heat, leading to an even distribution of temperature across the planet's surface. Venus's orbit and rotation have significant implications for its geology and atmospheric dynamics. The slow rotation allows for prolonged heating of the surface on the sunlit side, while the night side remains extremely hot due to the thick atmospheric insulation. The lack of significant seasonal variation on Venus means that the planet's weather patterns are primarily driven by its superrotational winds and atmospheric circulation. These winds create a dynamic and ever-changing environment despite the overall stability of the climate. Understanding Venus's orbit and rotation helps scientists compare it with Earth and other planets. The stark differences in rotation rate, direction, and axial tilt provide valuable insights into the diversity of planetary systems and the factors that influence their evolution. Space missions to Venus, such as NASA's Magellan mission and the European Space Agency's Venus Express, have provided detailed data on the planet's orbit, rotation, and atmosphere. These missions have expanded our knowledge and prompted further questions about Venus's unique characteristics. Future missions to Venus aim to explore these questions in greater depth. By studying Venus's orbit and rotation, scientists hope to uncover more about the planet's history, its geological and atmospheric processes, and the potential for past or present habitability. Venus's orbit and rotation are fundamental aspects of its identity. They shape the planet's environment and influence the conditions on its surface and atmosphere. Understanding these characteristics allows us to appreciate the complexities of Venus and its place in the solar system. Venus has been observed by humans since ancient times, often referred to as the morning star or evening star due to its bright appearance in the sky. These early observations led to a rich tapestry of myths and stories across different cultures. In ancient Mesopotamia, Venus was associated with the goddess Inanna, later known as Ishtar. She was the goddess of love, beauty, sex, fertility, and war. The planet's bright and prominent presence in the sky inspired many stories and religious practices centered around her. The ancient Greeks and Romans also linked Venus with deities. The Greeks called the planet Phosphorus when it appeared in the morning and Hesperus in the evening. Later, the Romans named it after their goddess of love and beauty, Venus, reflecting its stunning brightness. In Mesoamerican cultures, Venus was highly significant. The Mayans meticulously tracked its movements and associated it with the god Kukulkan, or Quetzalcoatl. They used Venus's cycles to time important events, such as wars and religious ceremonies, emphasizing its importance in their society. Ancient Chinese astronomers referred to Venus as the Great White and recorded its position meticulously. They noted its presence in various constellations and used these observations to refine their calendar and astrological systems. The Babylonians were among the first to document Venus's motion. Their records from the 2nd millennium BCE show a sophisticated understanding of the planet's appearances and disappearances, which they used for astrological predictions and divination. In Hindu mythology, Venus is known as Shukra, named after the sage Shukracharya. Shukra is considered a powerful planet in Vedic astrology, influencing wealth, pleasure, and reproduction. Its position in the sky is believed to affect personal fortunes and life events. Medieval Islamic astronomers made significant contributions to our understanding of Venus. Scholars like al-Battani and Ibn al-Haytham studied the planet's phases and apparent retrograde motion, improving astronomical models that later influenced European science. The Renaissance marked a turning point in the study of Venus with the advent of the telescope. Galileo Galilei's observations in the early 17th century revealed that Venus exhibited phases similar to the Moon, providing crucial evidence for the heliocentric model of the solar system. In the 18th and 19th centuries, astronomers continued to study Venus's atmosphere and phases. They speculated about its surface conditions and the possibility of life, although their understanding was limited by the observational technology of the time. Venus's thick clouds led to much speculation. Early astronomers like Giovanni Cassini and William Herschel noted its brightness and theorized about the nature of its atmosphere. Some believed it could be a tropical paradise beneath the clouds, fostering a wealth of imaginative ideas. By the 20th century, with the development of more advanced telescopes and space missions, our understanding of Venus shifted dramatically. Radar observations in the 1960s revealed its surface was extremely hot and hostile, debunking earlier myths of a lush, Earth-like world. Space missions like NASA's Mariner 2 in 1962 provided the first close-up data of Venus. These missions confirmed the harsh conditions, including high temperatures and pressures, which contrasted sharply with the myths and speculative theories that had persisted for centuries. The Soviet Union's Venera program in the 1960s and 70s successfully landed probes on Venus, providing detailed information about its surface and atmosphere. These missions were groundbreaking, showing a world far different from the idyllic visions of earlier cultures. Understanding the historical observations and myths about Venus offers a fascinating glimpse into humanity's evolving relationship with the cosmos. From divine symbols to subjects of scientific inquiry, Venus has captivated our imagination and driven our quest for knowledge, reflecting our changing perceptions of the universe. Space missions to Venus have significantly expanded our understanding of this enigmatic planet. The first successful mission was NASA's Mariner 2 in 1962, which flew by Venus and measured its surface temperature, confirming it was extremely hot. Following this, the Soviet Union launched the Venera program. Venera 3 in 1966 was the first spacecraft to reach Venus, although it failed before transmitting data. However, Venera 4 in 1967 successfully sent back information about the atmosphere, revealing it was mostly carbon dioxide. Venera 7 in 1970 became the first spacecraft to land on another planet and transmit data back to Earth. It confirmed surface temperatures around 470 degrees Celsius and high atmospheric pressures, which were much greater than anticipated. Venera 9 and Venera 10 in 1975 sent back the first images from the surface of Venus. These images showed a rocky terrain and offered the first glimpse of the Venusian landscape, providing invaluable insights into the planet's surface conditions. The Pioneer Venus project, launched by NASA in 1978, consisted of 2 missions, an orbiter and a multi-probe. The orbiter mapped the surface using radar, while the probes studied the atmosphere. This mission provided comprehensive data on Venus's atmospheric composition and surface characteristics. Magellan, launched by NASA in 1989, was one of the most successful missions to Venus. Using radar mapping, Magellan created detailed maps of the Venusian surface, revealing extensive volcanic plains, mountains, and complex tectonic features. The Soviet Vega program in 1984 included flybys of Venus en route to Halley's Comet. Vega 1 and Vega 2 dropped descent modules and balloons into Venus's atmosphere, providing valuable data on atmospheric composition and dynamics as they drifted through the clouds. ESA's Venus Express, launched in 2005, studied the atmosphere and surface of Venus for 8 years. It provided detailed information about atmospheric circulation, the greenhouse effect, and possible volcanic activity, greatly enhancing our understanding of Venusian weather patterns. The Akatsuki mission, launched by Japan's JAXA in 2010, focuses on atmospheric dynamics and weather. Despite initial challenges, it entered Venus's orbit in 2015 and has since provided valuable data on cloud structures, atmospheric circulation, and surface conditions. Venus missions have revealed that the planet's atmosphere is dominated by sulfuric acid clouds, contributing to its extreme greenhouse effect. These findings highlight the differences and similarities between Venus and Earth, offering insights into planetary atmospheres and climate change. The discovery of potential volcanic activity on Venus has intrigued scientists. Observations from Venus Express and other missions suggest that the planet may still be geologically active, with volcanic eruptions possibly occurring in recent geological history. Upcoming missions aim to build on these findings. NASA's Veritas and Da Vinci Plus missions, set for launch in the late 2020s, will investigate the geological history and atmospheric composition of Venus, providing deeper insights into its evolution and potential for past habitability. The Indian Space Research Organization, ISRO, plans to launch the Shukriyan-1 mission, focusing on surface and subsurface exploration as well as atmospheric studies. This mission will contribute to the growing body of knowledge about Venus's complex environment. NASA's Parker Solar Probe and ESA's Solar Orbiter, although primarily focused on studying the Sun, will also provide valuable data on Venus during their flybys. These missions will help refine our understanding of the interactions between Venus's atmosphere and solar wind. Space missions to Venus continue to transform our understanding of this hostile yet fascinating planet. Each mission builds upon the discoveries of previous ones, revealing new aspects of Venus's environment and history, and driving our quest to uncover the mysteries of our neighboring world. Earth's atmosphere is a complex and dynamic system that sustains life and influences climate. It is composed mainly of nitrogen, oxygen, argon, carbon dioxide, and trace gases. This mixture creates a protective layer around the planet, shielding it from harmful solar radiation. The atmosphere is divided into several layers, each with distinct characteristics. The troposphere is the lowest layer, where weather occurs and where most of the atmospheric mass is found. It extends from the Earth's surface to about 8 to 15 kilometers high. Above the troposphere lies the stratosphere, which contains the ozone layer. The ozone layer absorbs and scatters ultraviolet solar radiation, protecting living organisms from its harmful effects. This layer extends up to about 50 kilometers above the Earth. The mesosphere is the next layer, where temperatures decrease with altitude. It extends from 50 to 85 kilometers above the Earth and is where most meteorites burn up upon entering the Earth's atmosphere, creating meteor trails. Above the mesosphere is the thermosphere, a layer with very thin air and high temperatures. It extends from 85 kilometers to about 600 kilometers. This layer is where the auroras occur and where the International Space Station orbits. The exosphere is the outermost layer, gradually fading into space. It extends from about 600 kilometers to 10,000 kilometers. This region contains sparse hydrogen and helium atoms and marks the transition between Earth's atmosphere and outer space. Earth's climate system is driven by the energy from the sun. Solar radiation heats the Earth's surface, causing the air to warm and rise, creating weather patterns. The distribution of this heat varies due to the Earth's tilt, rotation, and the distribution of land and water. The greenhouse effect is a critical component of Earth's climate system. Greenhouse gases such as carbon dioxide, methane, and water vapor trap heat in the atmosphere, keeping the planet warm enough to support life. However, an increase in these gases can lead to global warming. Ocean currents play a significant role in regulating Earth's climate. The oceans absorb and store solar energy, distributing heat around the globe through currents like the Gulf Stream. These currents influence weather patterns and climate over long periods. The water cycle is another essential part of Earth's climate system. Water evaporates from the surface, forms clouds, and returns as precipitation. This continuous cycle redistributes heat and moisture, affecting weather and climate. Atmospheric circulation patterns, such as the Hadley cells, drive the movement of air around the planet. These patterns create prevailing winds and influence the distribution of climatic zones, from tropical rainforests to arid deserts. Human activities, particularly the burning of fossil fuels and deforestation, have significantly impacted Earth's atmosphere and climate systems. The increase in greenhouse gases has led to global warming, changing weather patterns, and more frequent extreme weather events. Climate change poses significant risks to natural ecosystems and human societies. Rising sea levels, increased frequency of heat waves, and shifts in agricultural productivity are just some of the challenges that result from a changing climate. Efforts to mitigate climate change focus on reducing greenhouse gas emissions and increasing the use of renewable energy sources. International agreements like the Paris Agreement aim to limit global temperature rise and promote sustainable practices. Understanding Earth's atmosphere and climate systems is crucial for predicting future changes and developing strategies to adapt to and mitigate the impacts of climate change. Scientific research and monitoring continue to play a vital role in enhancing our knowledge and informing policy decisions. Earth's geological features and processes are fundamental to shaping the planet's surface and supporting life. The crust, mantle, and core are the primary layers of Earth, each playing a crucial role in its geological dynamics. The crust is the outermost layer, divided into continental and oceanic types. Continental crust is thicker and less dense, composed mainly of granite. Oceanic crust is thinner and denser, primarily made of basalt. These crusts float on the more fluid upper mantle. Tectonic plates, large segments of the Earth's crust, move and interact at their boundaries. This movement is driven by convection currents in the mantle. The interactions between these plates create diverse geological features and phenomena, including earthquakes and volcanic activity. Plate boundaries are classified into three main types: divergent, convergent, and transform. At divergent boundaries, plates move apart, allowing magma to rise and form new crust, often seen at mid-ocean ridges. At convergent boundaries, plates collide, leading to the formation of mountains, deep ocean trenches, and volcanic arcs. Transform boundaries are where plates slide past each other horizontally. This lateral movement can cause significant earthquakes, as seen along the San Andreas Fault in California. The constant motion of tectonic plates reshapes the Earth's surface over millions of years. Volcanoes are prominent geological features formed by the movement of tectonic plates. They occur mainly along convergent and divergent boundaries, but can also form at hotspots. Volcanic activity brings molten rock, ash, and gases from the Earth's interior to the surface. Earthquakes result from the sudden release of energy along faults, fractures in the Earth's crust where movement has occurred. The energy release causes seismic waves that shake the ground, varying in intensity depending on the magnitude of the earthquake. Mountains are formed through tectonic processes such as the collision of continental plates. The Himalayas, the world's highest mountain range, are a result of the ongoing collision between the Indian and Eurasian plates. Mountains influence climate and weather patterns by affecting atmospheric circulation. Erosion and weathering are processes that break down rocks and minerals on the Earth's surface. Erosion involves the removal and transport of material by wind, water, ice, or gravity. Weathering, both chemical and physical, alters the composition and structure of rocks. Rivers and streams are powerful agents of erosion, carving valleys and shaping landscapes over time. They transport sediments that can eventually form deltas, where the river meets an ocean or lake. These processes contribute to the dynamic nature of Earth's surface. Glaciers, massive ice formations, shape the land through processes like glacial carving and deposition. As glaciers advance and retreat, they sculpt valleys, fjords, and moraines. The movement of glaciers also plays a role in the Earth's climate system by influencing ocean currents and sea levels. Deserts characterized by low precipitation feature unique geological processes such as wind erosion and dune formation. Wind carries and deposits sand, creating vast dune fields and eroding rock formations into intricate shapes. Caves and karst landscapes are formed by the dissolution of soluble rocks, such as limestone. Groundwater erodes these rocks, creating underground voids and drainage systems. Stalactites and stalagmites are common features in limestone caves, formed by the deposition of minerals from dripping water. Coastal processes driven by waves, tides, and currents shape shorelines and create features like beaches, cliffs, and barrier islands. The interaction between the ocean and the land is dynamic, continually reshaping coastlines through erosion and deposition. Geological processes are not only responsible for creating landscapes, but also for providing resources essential to human civilization. Minerals, fossil fuels, and groundwater are all products of geological processes, highlighting the importance of geology in our daily lives. Understanding geological features and processes is crucial for predicting natural hazards, managing natural resources, and studying the history of Earth. Geology provides insights into the planet's past, helping us to understand its present and anticipate its future. Life on Earth is a remarkable phenomenon that sets our planet apart from others in the solar system. The conditions that support life here are incredibly complex and finely tuned, creating an environment where diverse forms of life can thrive. One of the key factors supporting life on Earth is the presence of liquid water. Earth's distance from the Sun places it within the habitable zone, where temperatures allow water to exist in liquid form. Water is essential for all known forms of life, acting as a solvent in which biochemical reactions occur. Earth's atmosphere plays a crucial role in sustaining life. It provides oxygen for respiration, protects living organisms from harmful solar radiation, and helps regulate the planet's temperature through the greenhouse effect. The atmosphere's composition and structure are vital for maintaining conditions suitable for life. The diversity of life on Earth is astounding, ranging from microscopic bacteria to massive whales. This biodiversity is supported by a variety of habitats, from deep ocean trenches to mountain peaks. Each ecosystem has evolved to sustain a wide array of organisms, each adapted to its specific environment. Photosynthesis is a fundamental process that sustains life on Earth. Plants, algae, and certain bacteria convert sunlight into chemical energy, producing oxygen as a byproduct. This process forms the basis of the food chain, supporting life at all levels of the ecosystem. Earth's magnetic field provides essential protection for life. It deflects charged particles from the solar wind, preventing them from stripping away the atmosphere. This magnetic shield is crucial for maintaining the atmosphere's integrity and protecting living organisms from high-energy radiation. The planet's geological activity also contributes to the sustenance of life. Volcanic eruptions, plate tectonics, and the cycling of elements through the Earth's crust and atmosphere provide essential nutrients and create habitats that support diverse forms of life. The evolution of life on Earth has been driven by both gradual processes and sudden events. Natural selection, genetic mutations, and environmental changes have shaped the diversity of life over billions of years. Mass extinctions and evolutionary radiations have punctuated this history, leading to the rise and fall of various species. Human life is a unique aspect of Earth's biosphere. Humans have developed advanced cognitive abilities, complex social structures, and technologies that have transformed the planet. While humans are a part of Earth's biodiversity, they also have a profound impact on the environment and other species. The study of life on Earth provides insights into the potential for life elsewhere in the universe. By understanding the conditions that support life here, scientists can identify other planets and moons where similar conditions might exist, guiding the search for extraterrestrial life. The uniqueness of Earth's life forms lies not only in their biological characteristics, but also in their interactions with the environment. Ecosystems are intricate webs of interdependence, where each species plays a role in maintaining the balance of the whole system. Life on Earth has shown remarkable resilience, adapting to a wide range of environments and surviving through dramatic changes. From the deepest ocean trenches to the highest mountains, life has found a way to thrive, demonstrating its incredible versatility and tenacity. The presence of life on Earth has also influenced the planet's geology and atmosphere. Biological processes have contributed to the formation of sedimentary rocks, the cycling of elements, and the composition of the atmosphere. Life and Earth are inextricably linked, each shaping the other. Conservation of biodiversity is essential for maintaining the health of the planet. The loss of species and habitats threatens the balance of ecosystems and the services they provide, which are crucial for human survival and well-being. Protecting biodiversity is a responsibility that humans must embrace. Understanding the uniqueness of life on Earth enhances our appreciation of the planet and our place within its complex web of life. It underscores the importance of studying and preserving the natural world, ensuring that the remarkable phenomenon of life continues to thrive for future generations. Earth's magnetic field is a crucial feature that extends from the planet's interior into space, where it interacts with solar wind. This magnetic field is generated by the movement of molten iron and nickel in Earth's outer core, creating a dynamo effect. One of the primary functions of the magnetic field is to protect the planet from solar and cosmic radiation. The field deflects charged particles from the sun, known as the solar wind, preventing them from stripping away the atmosphere and exposing the surface to harmful radiation. The magnetic field creates the magnetosphere, a protective bubble around Earth. The magnetosphere shields the planet from solar wind, funneling charged particles toward the poles, where they cause auroras. These beautiful light displays are visible in the polar regions as the northern and southern lights. Earth's magnetic field is not static. It undergoes periodic reversals, where the magnetic north and south poles switch places. These geomagnetic reversals occur irregularly every few 100,000 years. Studying these reversals helps scientists understand the dynamics of Earth's interior. The magnetic field also aids in navigation for both humans and animals. Compasses align with Earth's magnetic field, providing a reliable means of orientation. Many migratory species, such as birds and sea turtles, use the magnetic field to navigate across vast distances. The interaction between the solar wind and the magnetic field can cause geomagnetic storms. These storms occur when solar wind disturbances compress the magnetosphere, leading to enhanced auroral activity and potentially disrupting satellite communications and power grids on Earth. Understanding the magnetic field is essential for space exploration. It protects astronauts and spacecraft from high-energy particles in space. Engineers design spacecraft shielding and mission planning to account for the effects of space weather influenced by the magnetic field. Research into Earth's magnetic field has practical applications in understanding other planets. By studying how Earth's dynamo works, scientists gain insights into the magnetic fields of other planets, such as Mars, which has a weak and patchy magnetic field, and Jupiter, with its powerful magnetic field. The magnetic field also influences Earth's climate over geological timescales. Variations in the magnetic field can affect the amount of cosmic radiation reaching the atmosphere, influencing cloud formation and, consequently, climate patterns. Paleomagnetism, the study of ancient magnetic fields recorded in rocks, provides valuable information about the history of Earth's magnetic field. By analyzing the magnetic properties of rocks, scientists can reconstruct the movements of tectonic plates and the history of geomagnetic reversals. Magnetic anomalies in the Earth's crust help in locating natural resources. These anomalies indicate variations in the magnetic properties of underground rock formations, aiding in the exploration of minerals, oil, and gas deposits. The magnetic field plays a role in protecting the ozone layer by preventing energetic particles from reaching the stratosphere. This protection helps maintain the ozone layer, which shields the planet from harmful ultraviolet radiation. Studying the magnetic field contributes to our understanding of Earth's interior. Seismology, combined with geomagnetic studies, reveals the structure and dynamics of the core, mantle, and crust, enhancing our knowledge of geological processes. Technological advancements in measuring the magnetic field, such as satellite missions like the European Space Agency's SWARM mission, provide high-resolution data on the field's structure and changes. This data is crucial for both scientific research and practical applications. The importance of Earth's magnetic field cannot be overstated. It protects the planet, supports navigation, influences climate, and provides insights into geological and space processes. Understanding and monitoring the magnetic field is essential for ensuring the well-being and advancement of life on Earth. Human impact on the planet has been profound and far-reaching. One of the most significant impacts is climate change, driven by the increased concentration of greenhouse gases in the atmosphere due to burning fossil fuels, deforestation, and industrial processes. Deforestation, particularly in tropical rainforests, has led to significant loss of biodiversity and disruption of ecosystems. Forests play a crucial role in carbon sequestration, and their removal accelerates climate change while destroying habitats for countless species. Urbanization and infrastructure development have transformed landscapes and altered natural processes. The expansion of cities and towns has led to habitat fragmentation, water pollution, and increased demand for resources impacting both local and global environments. Agriculture has reshaped vast areas of the planet, leading to soil degradation, water scarcity, and loss of biodiversity. The use of chemical fertilizers and pesticides has contaminated soil and water bodies, affecting ecosystems and human health. Overfishing has severely depleted fish populations in the world's oceans, disrupting marine ecosystems and threatening the livelihoods of communities dependent on fishing. Unsustainable fishing practices also cause habitat destruction, such as damage to coral reefs and seafloors. Pollution from industrial activities, agriculture, and urban runoff has contaminated air, water, and soil. Plastic pollution, in particular, has become a global crisis, with millions of tons of plastic waste entering the oceans each year, harming marine life and ecosystems. The burning of fossil fuels for energy has led to significant air pollution, contributing to respiratory diseases and other health problems. Emissions from vehicles, power plants, and industrial facilities release pollutants such as sulfur dioxide, nitrogen oxides, and particulate matter. Waste management is a growing challenge, with increasing amounts of solid waste generated by human activities. Inadequate waste disposal and recycling practices lead to environmental contamination and health hazards, especially in developing regions. Climate change has resulted in more frequent and severe weather events, such as hurricanes, floods, droughts, and wildfires. These events cause widespread damage, displacing communities and affecting ecosystems and economies. The extraction of natural resources, including mining and drilling for oil and gas, has led to environmental degradation. These activities can result in habitat destruction, water pollution, and increased greenhouse gas emissions, further contributing to climate change. Loss of biodiversity is one of the most critical impacts of human activity. Habitat destruction, pollution, climate change, and overexploitation of species have led to a dramatic decline in wildlife populations, threatening the stability of ecosystems and the services they provide. The introduction of invasive species by human activity has disrupted ecosystems and native species. Invasive species often outcompete, prey on, or bring diseases to native species, leading to declines or extinctions and altering ecosystem dynamics. Water resources are under immense pressure from human activities. Over-extraction of groundwater, pollution, and climate change have led to water scarcity in many regions, affecting agriculture, industry, and drinking water supplies. Efforts to mitigate human impact include transitioning to renewable energy sources such as solar and wind to reduce greenhouse gas emissions. Sustainable practices in agriculture, forestry, and fisheries aim to preserve ecosystems and biodiversity. Environmental awareness and conservation efforts are crucial for protecting the planet. Education, policy changes, and global cooperation are essential to address the challenges posed by human impact and to ensure a sustainable future for all life on Earth. Mars, known as the Red Planet, has distinct physical and atmospheric characteristics that make it a fascinating subject of study. Its reddish appearance is due to iron oxide, or rust, on its surface. Mars is about half the size of Earth, with a diameter of approximately 6,779 kilometers. Its gravity is roughly 38% that of Earth's, which significantly affects its atmosphere and surface features. The planet has a very thin atmosphere, composed mostly of carbon dioxide, with traces of nitrogen and argon. This thin atmosphere is unable to retain much heat, leading to significant temperature variations between day and night. Surface temperatures on Mars can vary widely, from about -125 degrees Celsius at the poles during winter to up to 20 degrees Celsius in equatorial regions during the day. Nighttime temperatures can plummet rapidly due to the thin atmosphere. Mars has the largest volcano in the solar system, Olympus Mons, which stands about 22 kilometers high. It also features Valles Marineris, a system of canyons that stretches over 4,000 kilometers, dwarfing the Grand Canyon. Dust storms are common on Mars and can cover the entire planet. These storms can last for days to weeks, impacting the surface and atmospheric conditions significantly. The fine dust particles are lifted by the winds, creating a reddish haze that can obscure the surface. Mars has polar ice caps composed of water and carbon dioxide ice. These caps expand and contract with the seasons, sublimating into the atmosphere during the summer and refreezing in the winter. The planet's axial tilt is similar to Earth's, at about 25 degrees, which gives Mars seasons. However, these seasons are about twice as long due to Mars's longer orbital period around the Sun, which takes about 687 Earth days. Mars lacks a global magnetic field, but it has localized magnetic fields in certain regions. These fields are remnants of an ancient global magnetic field that once protected the planet's atmosphere from solar wind erosion. The thin atmosphere means that liquid water cannot exist on the surface for long. However, there is evidence of ancient river valleys and lake beds, suggesting that liquid water was once abundant on Mars. The atmosphere is often hazy due to suspended dust particles. This haze can affect visibility and temperature, influencing the planet's weather and climate patterns. Mars's two small moons, Phobos and Deimos, are irregularly shaped and thought to be captured asteroids. Their surfaces are heavily cratered and they orbit close to Mars, with Phobos being so close that it orbits faster than Mars rotates. The surface of Mars features diverse geological formations, including impact craters, valleys, and ancient river channels. These formations provide evidence of a complex geological history influenced by volcanic activity, erosion, and possibly tectonic forces. The thin atmosphere and low gravity contribute to a high rate of meteoroid impacts, preserving craters for millions of years. These craters vary in size and are often surrounded by ejected materials. Understanding the physical and atmospheric characteristics of Mars is crucial for future exploration and the search for past or present life. These characteristics influence the design of missions, the selection of landing sites, and the development of technology for human exploration. Mars has long been a focus of the search for extraterrestrial life due to its potential for water. Evidence suggests that Mars once had liquid water on its surface, an essential ingredient for life as we know it. Satellite images have revealed ancient river valleys and lake beds, indicating that liquid water once flowed across the Martian surface. These features suggest that Mars had a much warmer and wetter climate in the past. The presence of clay minerals detected by orbiters indicates that water was present for extended periods. Clays form in the presence of water, and their discovery supports the idea of long-lasting liquid water on Mars. Rovers like Curiosity have found further evidence of ancient water. Curiosity discovered rounded pebbles and sedimentary layers, which are typically formed by flowing water. These findings point to ancient riverbeds that once carved through the Martian landscape. The discovery of recurring slope lineae, or dark streaks on the slopes of Martian craters and valleys, suggests that liquid water may still flow on Mars occasionally. These streaks appear to ebb and flow with the seasons, possibly indicating briny water flows. Mars Reconnaissance Orbiter detected hydrated salts in these recurring slope lineae. These salts lower the freezing point of water, allowing briny liquid to exist temporarily on the surface, even in the cold Martian environment. Evidence of ancient deltas and alluvial fans further supports the presence of standing bodies of water, like lakes or seas. These features are created by water carrying sediment and depositing it over time, forming layered deposits. Subsurface ice has been detected in various locations on Mars. Radar instruments on orbiters have identified vast reserves of water ice just beneath the surface, which could potentially be accessed by future missions. In 2018, scientists announced the detection of a subsurface lake of liquid water beneath the southern polar ice cap. This discovery, made using radar data, suggests that liquid water might still exist beneath the surface, protected from the harsh conditions above. The presence of water ice at the poles is well documented. Seasonal changes cause this ice to sublimate into the atmosphere and then refreeze, indicating active water cycles on Mars. Mars rovers have also detected minerals that form in the presence of water, such as sulfates and opal. These discoveries indicate that water once interacted with the Martian surface, altering its mineral composition. The potential for past or present life on Mars is a driving force behind exploration. Liquid water is crucial for life, and the evidence of its past presence increases the likelihood that Mars could have supported microbial life. Astrobiologists study extremophiles on Earth, organisms that live in extreme environments, to understand how life might survive on Mars. Similarities between these harsh Earth environments and conditions on Mars provide insights into the potential for Martian life. Future missions aim to explore this potential further. NASA's Perseverance rover is searching for signs of ancient microbial life, collecting samples that will be returned to Earth for detailed analysis. These efforts are crucial for understanding Mars's habitability. The ongoing search for water and life on Mars is part of a broader effort to understand our place in the universe. Discovering past or present life on Mars would have profound implications for biology, geology, and our understanding of life's potential beyond Earth. Mars is home to some of the most striking surface features in the solar system, including the largest volcano and one of the deepest canyon systems. Olympus Mons is the tallest volcano in the solar system, towering about 22 kilometers above the surrounding plains. This shield volcano is about 600 kilometers in diameter, roughly the size of the state of Arizona. The caldera at the summit of Olympus Mons is approximately 80 kilometers wide, indicating the massive scale of volcanic activity that formed it. The slopes of this volcano are gentle, spreading out over a vast area. Tharsis is a volcanic plateau on Mars that hosts several large volcanoes, including Olympus Mons Ascrius Mons, Pavonis Mons, and Arsia Mons. These volcanoes are all shield volcanoes, characterized by their broad, dome-like profiles. The Tharsis region's volcanic activity has had a significant impact on Mars's geology, contributing to the planet's tectonic and volcanic history. The region is believed to have formed from upwelling of magma that created the plateau and its towering volcanoes. Valles Marineris is one of the most extensive canyon systems in the solar system, stretching over 4,000 kilometers long, 200 kilometers wide, and up to 7 kilometers deep. This canyon is roughly 10 times longer and 5 times deeper than the Grand Canyon. The formation of Valles Marineris is thought to be related to the tectonic stresses that created the Tharsis Plateau. As the Tharsis region uplifted, it caused the crust to stretch and crack, forming the immense canyon system. Habes Kasma, a part of the Valles Marineris system, features a central mesa that rises nearly to the canyon's rim. This mesa is a unique geological formation, providing insights into the sedimentary and erosional processes on Mars. The presence of layered sedimentary rocks within Valles Marineris suggests a history of water flow. These layers may have been deposited by ancient lakes or streams, indicating that liquid water once played a significant role in shaping the canyon. In addition to its massive volcanoes and canyons, Mars has numerous impact craters. The largest, Hellas Planitia, is about 2,300 kilometers in diameter and 7 kilometers deep. This impact basin is one of the most prominent features on the Martian surface. Other notable craters include Gale Crater, which hosts the Curiosity rover, and Jezero Crater, the landing site of the Perseverance rover. These craters provide valuable information about Mars's geological history and potential past habitability. Mars also features extensive lava plains, particularly in the northern lowlands. These plains are believed to be the result of widespread volcanic activity that resurfaced large areas of the planet. The planet's surface is marked by various tectonic features, such as grabens and rift valleys, formed by the stretching and cracking of the crust. These features provide evidence of the tectonic forces that have shaped Mars over billions of years. Aeolus Mons, also known as Mount Sharp, is a central peak in Gale Crater. The mountain rises about 5.5 kilometers above the crater floor, with layers of sediment that record the environmental history of Mars. Understanding the surface features of Mars, from its towering volcanoes to its deep canyons, is crucial for unraveling the planet's geological and climatic history. These features tell a story of a planet that was once geologically active and may have had conditions suitable for life. Mars exploration missions have revolutionized our understanding of the Red Planet, revealing its complex history and potential for life. The journey began with Mariner 4, launched by NASA in 1964, which was the first spacecraft to fly by Mars and send back images of its surface. Mariner 9, launched in 1971, became the first spacecraft to orbit another planet. It mapped nearly the entire Martian surface, discovering vast volcanoes, canyon systems, and evidence of ancient riverbeds, providing a wealth of data that reshaped our understanding of Mars. The Viking program, consisting of Viking 1 and Viking 2, was a landmark in Mars exploration. Launched in 1975, each mission included an orbiter and a lander. The Viking landers conducted the first successful landings on Mars, performing experiments to search for signs of life and analyze the soil and atmosphere. Pathfinder, launched in 1996, marked the beginning of a new era with the deployment of the Sojourner rover. This mission demonstrated the feasibility of rover exploration, providing valuable data on the Martian terrain and atmosphere while showcasing innovative technology. The Mars Global Surveyor, launched in 1996, mapped the entire planet with high-resolution cameras and provided detailed topographical and compositional data. Its findings included evidence of liquid water activity and a better understanding of Mars's magnetic field. Spirit and Opportunity, twin rovers of the Mars Exploration Rover mission, landed on Mars in 2004. They were designed to search for and characterize a wide range of rocks and soils for clues to past water activity. Both rovers made groundbreaking discoveries, including finding signs of ancient water flows. The Phoenix mission, launched in 2007, focused on the northern polar region of Mars. It confirmed the presence of water ice just below the surface and studied the planet's climate and geology, providing critical data on the potential for habitability. Curiosity, part of NASA's Mars Science Laboratory mission, landed in Gale Crater in 2012. Equipped with advanced scientific instruments, Curiosity has been exploring the Martian surface, analyzing soil and rock samples, and assessing past environmental conditions that could have supported microbial life. The Mars Reconnaissance Orbiter, launched in 2005, has been providing high-resolution imagery and data on Mars's atmosphere, weather, and surface conditions. Its observations have been crucial for planning future missions and identifying potential landing sites. India's Mars Orbiter mission, also known as Mangalyaan, was launched in 2013 and successfully entered Mars orbit in 2014. This mission made India the first country to reach Mars orbit on its first attempt, and it has provided valuable data on the Martian surface and atmosphere. The ExoMars program, a collaboration between the European Space Agency and Roscosmos, aims to search for signs of past life on Mars. The Trace Gas Orbiter, launched in 2016, has been studying the atmosphere and searching for trace gases that could indicate biological or geological activity. NASA's InSight mission, launched in 2018, focuses on studying the interior of Mars. Its seismometer has detected Marsquakes, providing insights into the planet's internal structure and composition and improving our understanding of its geological history. Perseverance, the most advanced rover to date, landed in Jezero Crater in 2021. It is searching for signs of ancient life and collecting samples that will be returned to Earth by future missions. Perseverance also carries the Ingenuity helicopter, which has successfully demonstrated powered flight on Mars. China's Tianwen-1 mission, which includes an orbiter, lander, and rover, successfully reached Mars in 2021. The Zhurong rover is exploring the surface, studying the geology, atmosphere, and climate, marking China's significant achievement in Mars exploration. These missions, past and present, continue to deepen our understanding of Mars, paving the way for future human exploration. They provide crucial data that helps scientists piece together the planet's history, its potential for life, and its suitability for future missions, including human landings. Future plans for human exploration of Mars are ambitious and involve multiple phases of development and testing. NASA, along with international and commercial partners, is spearheading efforts to land humans on Mars within the next decade. The Artemis program is a crucial stepping stone for Mars exploration. By returning humans to the Moon and establishing a sustainable presence there, NASA aims to develop and test technologies and systems needed for the longer journey to Mars. One of the primary goals is to build the Lunar Gateway, a space station orbiting the Moon. This outpost will serve as a staging point for missions to Mars, allowing astronauts to prepare and conduct long-duration missions in deep space. Mars missions will require advanced propulsion systems to reduce travel time and improve safety. NASA is developing nuclear thermal propulsion and solar electric propulsion technologies to enable faster and more efficient travel to Mars. The Mars Base Camp concept envisions a crewed mission to Mars orbit, where astronauts can remotely operate robots on the surface before landing. This approach reduces the risk and allows for extensive scientific exploration of multiple sites. Landing humans on Mars will require significant advancements in entry, descent, and landing technologies. NASA is testing inflatable heat shields and precision landing systems to safely deliver large payloads, including habitats and rovers, to the Martian surface. Sustainable life support systems are essential for long-duration missions. Researchers are developing closed-loop systems that recycle air, water, and waste, and exploring ways to produce food using Martian resources. In situ resource utilization, or ISRU, is a key focus for Mars missions. Techniques to extract water from the Martian soil and convert carbon dioxide from the atmosphere into oxygen and fuel are being developed to reduce reliance on Earth-based supplies. Habitat modules designed for Mars will need to protect astronauts from radiation, extreme temperatures, and dust storms. Concepts include inflatable habitats, underground bases, and 3D-printed structures using Martian regolith. Robotic missions will continue to pave the way for human exploration. Upcoming missions will focus on identifying safe landing sites, mapping resources, and testing technologies that will support human missions. International collaboration is crucial for the success of Mars exploration. Agencies like ESA, Roscosmos, CNSA, and private companies like SpaceX are all working towards sending humans to Mars, and partnerships will enhance mission capabilities and reduce costs. SpaceX's Starship is a fully reusable spacecraft designed for deep space missions, including Mars. With plans for multiple cargo and crew missions, Starship aims to establish a human presence on Mars, supporting NASA's goals and enabling commercial opportunities. The journey to Mars will involve addressing numerous health risks. Prolonged exposure to microgravity and space radiation poses significant challenges, and researchers are developing countermeasures to protect astronauts during the long mission. Simulated Mars habitats on Earth, such as those in Hawaii and Antarctica, provide valuable data on the psychological and logistical aspects of long-term space missions. These analog missions help refine life support systems, mission protocols, and crew dynamics. Public engagement and education are vital for sustaining interest and support for Mars exploration. Initiatives to involve the public, students, and educators in mission planning and STEM education will inspire the next generation of explorers and scientists. The dream of human exploration of Mars is becoming increasingly tangible. With continued advancements in technology, international cooperation, and sustained commitment, humanity is poised to take its first steps on the Red Planet, opening a new chapter in space exploration and discovery. Jupiter is the largest planet in our solar system, with a composition and structure that set it apart from the terrestrial planets. It is primarily composed of hydrogen and helium, similar to the Sun. The planet's atmosphere is divided into several layers, with the uppermost layer consisting mostly of molecular hydrogen and helium, along with trace amounts of methane, ammonia, water vapor, and other gases. Jupiter's atmosphere is known for its colorful bands and turbulent storms. The bands are created by strong east-west winds that can reach speeds of up to 400 kilometers per hour. These bands are divided into light-colored zones and darker belts. The Great Red Spot, a massive storm system larger than Earth, is one of the most distinctive features of Jupiter's atmosphere. This anticyclonic storm has persisted for at least 400 years, possibly much longer. Beneath the visible clouds, the pressure and temperature increase dramatically. The atmosphere transitions into a layer of liquid hydrogen as the pressure becomes high enough to force hydrogen molecules into a liquid state. Further down, the liquid hydrogen layer gradually transitions into metallic hydrogen. In this state, hydrogen behaves like a metal, conducting electricity and generating Jupiter's powerful magnetic field. The core of Jupiter is believed to be composed of heavier elements, including rock and metal. Estimates suggest the core may be 10 to 20 times the mass of Earth, although its exact composition and size remain subjects of scientific investigation. Jupiter's immense magnetic field is the strongest of any planet in the solar system, extending up to 7 million kilometers toward the Sun and almost reaching Saturn's orbit on the opposite side. This magnetic field traps charged particles and creates intense radiation belts. The planet's rapid rotation, completing a full spin approximately every 10 hours, contributes to its oblate shape. This rotation causes the equator to bulge outward, making Jupiter wider at the equator than at the poles. Jupiter emits more heat than it receives from the Sun. This excess heat is generated by the gradual gravitational compression of the planet, known as Kelvin-Helmholtz contraction. This process releases energy, contributing to Jupiter's internal heat. The planet's magnetosphere is a vast region dominated by its magnetic field. It influences the movement of charged particles, creating spectacular auroras at the poles. These auroras are much more powerful than those on Earth. Jupiter has a faint ring system composed primarily of dust particles ejected from its moons by micrometeoroid impacts. These rings are difficult to see from Earth and were first discovered by the Voyager spacecraft. The intense radiation environment around Jupiter poses significant challenges for spacecraft. Instruments must be specially designed to withstand the high levels of radiation to study the planet and its moons. Jupiter's strong gravitational influence affects the orbits of other objects in the solar system. It has played a crucial role in shaping the asteroid belt and protecting the inner planets from frequent comet impacts by capturing or deflecting potential threats. Understanding Jupiter's composition and structure provides insights into the formation and evolution of gas giants. Studying this giant planet helps scientists learn more about the processes that govern the formation of planetary systems, both in our solar system and beyond. The Great Red Spot is one of Jupiter's most iconic features, a massive storm larger than Earth that has been raging for centuries. This anticyclonic storm is located in Jupiter's southern hemisphere and is characterized by its reddish hue and swirling cloud patterns. The storm's dimensions are staggering. It measures about 16,000 kilometers in width, although it has been gradually shrinking over the past few decades. Despite this shrinkage, the Great Red Spot remains a dominant and persistent feature of Jupiter's atmosphere. The exact cause of the red color is still a subject of research. It is thought to result from complex chemical reactions involving the planet's atmospheric compounds, possibly including phosphorus, sulfur, and organic molecules, influenced by ultraviolet radiation from the Sun. The Great Red Spot's wind speeds can reach up to 432 kilometers per hour. These winds circulate around the storm's center, creating a high-pressure region that contributes to its longevity and stability within the dynamic Jovian atmosphere. Jupiter is home to other impressive storms as well. Smaller but still significant, the planet's atmosphere is dotted with various white ovals and brown barges, which are cyclonic systems that can last for many years, adding to the turbulent and ever-changing nature of the planet. White ovals are typically high-pressure systems found at various latitudes on Jupiter. They appear bright due to their higher altitude clouds, which reflect more sunlight. These storms can merge, forming larger systems or dissipate over time. Brown barges are elongated, brown-colored storms found mainly in Jupiter's northern hemisphere. They are lower-pressure systems compared to the white ovals and are less reflective, making them appear darker against the surrounding cloud tops. The South Equatorial Belt disturbance is another notable storm feature. It is a recurring event where the southern equatorial belt fades and reappears, involving complex interactions between Jupiter's atmospheric layers and jet streams. Jupiter's polar regions host unique storm patterns, including cyclones arranged in geometric patterns. NASA's Juno mission discovered clusters of cyclones at both poles, forming pentagonal and hexagonal shapes unlike anything seen on other planets. These polar cyclones are massive, each spanning thousands of kilometers. They are densely packed and exhibit stable configurations, raising intriguing questions about the atmospheric dynamics that sustain these geometric patterns. The energy that drives Jupiter's storms comes from both the Sun and the planet's internal heat. The planet radiates more energy than it receives, due to the heat generated by gravitational compression and possibly ongoing slow contraction of the planet's interior. Jupiter's fast rotation, with a day lasting just about 10 hours, plays a crucial role in shaping its atmospheric dynamics. The rapid spin creates strong jet streams that run parallel to the equator, leading to the formation of distinct bands and storm systems. The interactions between these jet streams and storms contribute to the complex and dynamic weather patterns observed on Jupiter. The belts and zones shift and change over time, influencing the formation and evolution of storm systems. Understanding the Great Red Spot and other Jovian storms provides valuable insights into atmospheric processes that can be applied to other gas giants in our solar system and exoplanets. These studies help scientists develop models of planetary atmospheres under extreme conditions. The continuous observation of Jupiter's storms by spacecraft like Juno and the Hubble Space Telescope enhances our knowledge of the planet's meteorology. These missions provide detailed data on the structure, composition, and dynamics of Jupiter's atmosphere, deepening our understanding of the largest planet in the solar system. Jupiter's moons, especially the Galilean satellites, are some of the most fascinating objects in the solar system. Discovered by Galileo Galilei in 1610, these four largest moons, Io, Europa, Ganymede, and Callisto, have unique characteristics that provide insights into planetary formation and the potential for life beyond Earth. Io, the innermost of the Galilean moons, is the most volcanically active body in the solar system. Its surface is dotted with hundreds of volcanoes, some of which erupt with lava fountains reaching up to 500 kilometers high. This intense volcanic activity is driven by tidal heating, caused by the gravitational pull of Jupiter and the other Galilean moons. Europa, slightly smaller than Earth's moon, is one of the prime candidates in the search for extraterrestrial life. Beneath its smooth, icy surface lies a subsurface ocean of liquid water, kept warm by tidal heating. The icy crust is fractured and shows evidence of geologic activity, suggesting that the ocean could be in contact with the moon's rocky mantle, providing the necessary conditions for life. Ganymede, the largest moon in the solar system, is even bigger than the planet Mercury. It has a magnetic field, a feature unique among moons, likely generated by a partially liquid iron-nickel core. Ganymede's surface is a mix of two types of terrain: dark, heavily cratered regions and lighter, grooved areas, indicating tectonic activity. Callisto, the outermost Galilean moon, is heavily cratered and ancient, with a surface that has remained largely unchanged for billions of years. Unlike the other Galilean moons, Callisto shows little evidence of geological activity, making it a valuable record of the early solar system. The discovery of the Galilean satellites provided the first evidence that not all celestial bodies orbit Earth, supporting the Copernican model of a heliocentric solar system. These moons also demonstrated the diversity of planetary bodies, each with its own unique environment and geological history. Io's volcanic activity results from the immense tidal forces exerted by Jupiter and the other moons. These forces flex Io's interior, generating heat through friction and driving the constant resurfacing of its landscape with lava flows and volcanic plumes. Europa's icy surface features cracks and ridges formed by the movement of its ice shell. Scientists believe that the subsurface ocean interacts with the surface through these fractures, potentially allowing for the exchange of chemicals and energy, which are vital for sustaining life. Ganymedes' magnetic field creates auroras, similar to those on Earth. These auroras have been used to detect the presence of a subsurface ocean, which could contain more water than all of Earth's oceans combined, highlighting the Moon's potential for harboring life. Callisto's lack of geological activity and heavily cratered surface suggest it has not undergone significant internal heating. However, there is evidence of a subsurface ocean beneath its icy crust, which could have implications for our understanding of where life might exist in the solar system. The interactions between the Galilean moons and Jupiter create complex gravitational dynamics, influencing their orbits and internal structures. These interactions also affect the Moon's geologic and potentially biologic processes, making them a rich area of study. Exploration of the Galilean satellites has been primarily conducted by spacecraft like the Galileo orbiter, which provided detailed observations of their surfaces and environments. Future missions, such as the European Space Agency's JUICE mission and NASA's Europa Clipper, aim to explore these moons in greater detail. JUICE, the Jupiter Icy Moons Explorer, will focus on Ganymede, Callisto, and Europa, studying their oceans, surfaces, and potential habitability. Europa Clipper will specifically target Europa, conducting multiple flybys to analyze its ice shell and subsurface ocean. The study of Jupiter's moons not only advances our understanding of the Jovian system, but also informs our search for habitable environments elsewhere in the galaxy. By exploring these diverse worlds, we gain insights into the conditions that could support life and the processes that shape planetary systems. The Galilean satellites continue to captivate scientists and the public alike. Their unique characteristics and potential for harboring life make them prime targets for future exploration, promising to reveal more about the mysteries of our solar system and the potential for life beyond Earth. Jupiter's magnetosphere is the largest and most powerful of any planet in the solar system. It extends up to 7 million kilometers toward the Sun and nearly reaches Saturn's orbit in the opposite direction. This immense magnetosphere is generated by the rapid rotation of Jupiter's metallic hydrogen core. The movement of conductive material within this core produces a strong magnetic field, much stronger than Earth's. Within Jupiter's magnetosphere, charged particles from the solar wind and from volcanic eruptions on Io are trapped. These particles create intense radiation belts, similar to Earth's Van Allen belts, but far more powerful. The inner radiation belts are especially hazardous. They contain high-energy electrons and ions that can damage spacecraft and pose significant risks to instruments and potential human explorers. Jupiter's magnetosphere is highly dynamic, influenced by the solar wind and the planet's rotation. This creates a complex system of currents and magnetic field lines that can change rapidly, leading to variations in the intensity of the radiation belts. Auroras at Jupiter's poles are some of the most spectacular displays in the solar system. These auroras are produced by particles accelerating along magnetic field lines and colliding with Jupiter's atmosphere, releasing energy as light. The interaction between Jupiter's magnetosphere and its moons creates unique phenomena. For instance, Io's volcanic activity releases sulfur dioxide gas, which is ionized and forms a torus of plasma that encircles Jupiter. This Io plasmatoris feeds the magnetosphere with charged particles, contributing to the radiation belts and affecting the magnetic environment. The interaction between Io and the magnetosphere also generates intense electrical currents known as Io flux tubes. Ganymede, the largest of Jupiter's moons, has its own magnetic field, which creates a mini magnetosphere within Jupiter's larger magnetosphere. This interaction produces unique auroral features on Ganymede. The study of Jupiter's magnetosphere provides insights into the behavior of magnetic fields and charged particles in extreme environments. It also helps scientists understand the magnetospheres of other planets, both within our solar system and around other stars. Spacecraft such as Galileo and Juno have provided detailed data on Jupiter's magnetosphere. Juno, in particular, has mapped the magnetic field with unprecedented precision, revealing complex structures and variations. The intense radiation environment poses challenges for spacecraft design. Instruments must be shielded to withstand the high-energy particles, and mission planners must carefully navigate these hazardous regions. Understanding Jupiter's magnetosphere is also crucial for the safety of future missions. Any potential human exploration of Jupiter or its moons will need to account for the extreme radiation levels and develop strategies to mitigate exposure. The influence of Jupiter's magnetosphere extends far beyond the planet itself. It affects the behavior of the solar wind and shapes the space environment in the outer solar system, playing a significant role in the dynamics of our cosmic neighborhood. Studying Jupiter's magnetosphere and radiation belts not only enhances our knowledge of the largest planet in our solar system, but also contributes to our understanding of fundamental processes that occur throughout the universe. These insights help us appreciate the complexities and wonders of planetary science. Exploration missions to Jupiter have greatly expanded our understanding of this giant planet and its diverse moons. The first mission to provide close-up images was Pioneer 10, launched by NASA in 1972. It sent back the first detailed images of Jupiter's atmosphere and magnetosphere. Pioneer 11 followed in 1973, providing additional data on Jupiter's magnetic field and radiation environment. These early missions paved the way for more advanced exploration. Voyager 1 and Voyager 2, launched in 1977, made significant contributions. They captured detailed images of Jupiter's clouds, discovered rings around the planet, and revealed the complex structures of its moons. Voyager missions also provided stunning images of the Great Red Spot and identified volcanic activity on Io, changing our understanding of the Jovian system. These discoveries highlighted the dynamic and diverse nature of Jupiter and its moons. The Galileo orbiter, launched in 1989, was the first to orbit Jupiter. It provided in-depth studies of the planet and its major moons, including detailed observations of Europa's icy surface and potential subsurface ocean. Galileo discovered evidence of a liquid ocean beneath Europa's ice crust, indicating the potential for habitable environments. It also conducted close flybys of Ganymede and Callisto, revealing their unique geological features and magnetic fields. The orbiter studied Jupiter's atmosphere, including its storms, lightning, and cloud composition. It also confirmed the presence of ammonia clouds and measured the heat emanating from the planet's interior. In 2000, the Cassini spacecraft performed a flyby of Jupiter on its way to Saturn. It captured high-resolution images and data, enhancing our understanding of Jupiter's atmosphere and rings. NASA's Juno mission, launched in 2011, is currently studying Jupiter's interior, atmosphere, and magnetosphere. Juno's detailed measurements are helping scientists understand the planet's composition, gravity field, and magnetic environment. Juno's findings have revealed the complexity of Jupiter's magnetic field, which is far more irregular and varied than previously thought. It also provided insights into the deep atmospheric dynamics, showing the structure and depth of the planet's zones and belts. The mission has also focused on the polar regions, capturing stunning images of the auroras and cyclones at the poles. These observations have provided new insights into Jupiter's atmospheric processes and magnetospheric interactions. Future missions to the Jovian system include the European Space Agency's JUICE mission, set to launch in 2023. JUICE will focus on studying Ganymede, Europa, and Callisto, aiming to explore their potential for habitability and understand their interactions with Jupiter's magnetosphere. NASA's Europa Clipper, scheduled for launch in the 2020s, will conduct detailed reconnaissance of Europa's ice shell and subsurface ocean. This mission aims to assess the Moon's potential for supporting life and identify sites for future exploration. The exploration of Jupiter has revolutionized our understanding of the largest planet in our solar system. Each mission has built upon the discoveries of previous ones, revealing the complexities of Jupiter's atmosphere, magnetic field, and moons. These missions have not only expanded our knowledge of Jupiter, but also provided insights into the processes that shape planetary systems. The ongoing exploration continues to inspire scientific inquiry and curiosity, pushing the boundaries of what we know about our cosmic neighborhood. Saturn, the second-largest planet in our solar system, is known for its stunning ring system. It has a diameter of about 116,460 kilometers, making it almost 10 times wider than Earth. Despite its size, Saturn is less dense than water, indicating it is composed primarily of hydrogen and helium. The planet's atmosphere is divided into several layers, each with distinct properties. The outermost layer is mostly hydrogen and helium, with traces of methane, ammonia, and other gases. These gases give Saturn its pale, yellow hue. Saturn's atmosphere features strong winds and storms, similar to Jupiter's. Wind speeds can reach up to 1,800 kilometers per hour near the equator. These winds contribute to the banded appearance of the planet, with zones and belts of varying colors and compositions. One of the most striking features of Saturn's atmosphere is the hexagon-shaped storm at the North Pole. This persistent hexagonal wave pattern is unlike anything seen on other planets and has puzzled scientists since its discovery. Beneath the outer layers of gas, Saturn has a thick layer of metallic hydrogen. This layer is created under the immense pressure and temperature within the planet, where hydrogen behaves like a metal and conducts electricity. Saturn's magnetic field is generated by the movement of metallic hydrogen in its interior. Although not as strong as Jupiter's, Saturn's magnetic field is still much more powerful than Earth's. It traps charged particles and creates radiation belts around the planet. The planet's core is believed to be composed of rock and metal, surrounded by a layer of ice. Estimates suggest the core could be 9 to 22 times the mass of Earth. The heat generated by the core contributes to Saturn's overall energy output. Saturn emits more energy than it receives from the Sun. This excess energy is due to the Kelvin-Helmholtz mechanism, where gravitational compression generates heat. This process keeps Saturn's interior warm and drives atmospheric dynamics. The cloud layers in Saturn's atmosphere are arranged in bands parallel to the equator. These bands are composed of ammonia ice, ammonium hydrosulfide, and water ice, each creating clouds at different altitudes. Storms on Saturn can be incredibly large and last for extended periods. The Great White Spot is a massive storm that appears roughly every 30 years. These storms can encircle the planet and significantly impact the atmosphere. The rings of Saturn are composed primarily of ice particles, with some rock and dust. They span up to 282,000 kilometers from the planet, but are only about 10 meters thick. The rings are divided into several sections, named alphabetically in the order they were discovered. The main rings are labeled A, B, and C, with the Cassini division separating the A and B rings. These rings contain numerous gaps and divisions created by the gravitational influence of Saturn's moons and complex orbital resonances. The atmosphere of Saturn is also home to intricate cloud patterns and jet streams. The varying wind speeds and chemical compositions create a dynamic and ever-changing environment, offering a glimpse into the complexities of gas giant atmospheres. Observations from missions like Voyager, Cassini, and the Hubble Space Telescope have provided detailed images and data about Saturn's physical characteristics and atmospheric behavior. These missions have significantly enhanced our understanding of the planet and its unique features. Saturn's atmosphere and physical characteristics reveal much about the processes at work in gas giants. By studying Saturn, scientists gain insights into the formation and evolution of our solar system and the dynamic processes that govern these distant, majestic worlds. Saturn's iconic ring system is one of the most spectacular features in the solar system. Composed primarily of ice particles with some rock and dust, the rings span up to 282,000 kilometers from the planet. The rings are divided into several sections, named alphabetically in the order they were discovered. The main rings are labeled A, B, and C, with the Cassini division separating the A and B rings. The Cassini division is a 800-kilometer wide gap caused by the gravitational influence of Saturn's moon Mimas. This division and other gaps within the rings result from orbital resonances with Saturn's moons. The rings are incredibly thin, averaging about 10 meters in thickness. Despite their vast horizontal spread, the rings are so thin that they almost disappear when viewed edge-on from Earth. The particles in the rings range in size from tiny grains of dust to large chunks up to several meters across. These particles are thought to be remnants of comets, asteroids, or shattered moons that were torn apart by Saturn's gravity. The bright, reflective nature of the rings is due to their high ice content. The ice particles reflect sunlight, making the rings visible from Earth and creating their striking appearance. The rings are constantly changing due to the gravitational interactions with Saturn's moons. These interactions create waves, gaps, and ringlets, resulting in a dynamic and complex structure. Saturn's moon, Enceladus, plays a significant role in the E-ring, the outermost of the main rings. Ice geysers on Enceladus eject particles that replenish and maintain this diffuse ring. The discovery of propellers within the rings has provided insights into the formation of moons and planetary systems. These propeller-shaped gaps are caused by larger ring particles that perturb the surrounding ring material. The rings also contain transient features such as spokes, which are radial markings that appear and disappear. These spokes are believed to be caused by the interaction of charged particles with Saturn's magnetic field. Observations from the Cassini spacecraft have greatly enhanced our understanding of the ring system. Cassini provided detailed images and data, revealing the fine structure and composition of the rings. Cassini's grand finale involved a series of daring dives between Saturn and its rings, providing unprecedented close-up views and measurements. This phase of the mission revealed new details about the ring's mass, age, and dynamics. The age of Saturn's rings is still debated. Some evidence suggests they are relatively young, possibly forming within the last 100 million years, while other evidence indicates they could be as old as the planet itself. The rings may eventually disappear. Over time, ring particles gradually spiral into Saturn due to the planet's gravitational pull and interactions with the magnetosphere. This process, known as ring rain, will deplete the rings over millions of years. Understanding Saturn's rings not only provides insights into the planet's history, but also offers a glimpse into the processes that shape planetary rings and disks throughout the universe. The study of Saturn's rings continues to captivate scientists and astronomers, revealing the dynamic beauty of our solar system. Titan, Saturn's largest moon, is one of the most intriguing bodies in the solar system. With a thick atmosphere primarily composed of nitrogen and methane, Titan is the only moon known to have a substantial atmosphere. Titan's surface is remarkably Earth-like, with lakes, rivers, and seas of liquid methane and ethane. The Huygens probe, which landed on Titan in 2005, provided direct evidence of this liquid activity and captured images of a landscape shaped by weather and erosion. Beneath Titan's icy crust lies a subsurface ocean of liquid water. This ocean, potentially interacting with organic molecules, raises the possibility of life existing in some form beneath the surface. Titan experiences a methane cycle similar to Earth's water cycle, with methane evaporating, forming clouds, and precipitating as rain. This cycle drives weather patterns and creates a dynamic environment on Titan's surface. Enceladus, another of Saturn's major moons, is famous for its geysers that spew water ice and organic molecules from its south polar region. These geysers are powered by tidal heating from Saturn's gravitational pull. The discovery of Enceladus's geysers by the Cassini spacecraft revealed that the moon has a subsurface ocean beneath its icy crust. This ocean is believed to be in contact with Enceladus's rocky core, creating conditions that could potentially support microbial life. The geysers eject material into space, creating the E-ring around Saturn. Analysis of the ejected material by Cassini detected water vapor, ice particles, salts, and organic compounds, suggesting a chemically rich environment. Enceladus's surface is covered in fresh, clean ice, making it one of the most reflective objects in the solar system. The lack of impact craters indicates ongoing resurfacing, driven by internal geologic activity. The heat necessary to sustain Enceladus's subsurface ocean and geysers likely comes from tidal forces exerted by Saturn and its moons. These forces cause the moon's interior to flex and heat up, driving the observed geologic activity. Both Titan and Enceladus are prime targets in the search for extraterrestrial life due to their subsurface oceans and potential for habitable environments. Future missions aim to explore these moons further and investigate their potential for supporting life. The Dragonfly mission, set to launch in the mid-2020s, will send a drone to Titan to study its surface and atmosphere in greater detail. Dragonfly will explore multiple sites, sampling Titan's organic chemistry and assessing its habitability. For Enceladus, proposed missions like the Enceladus Life Finder and the Enceladus Orbilander would focus on analyzing the plumes in greater detail, searching for signs of biological activity and studying the moon's ocean composition. Studying Titan and Enceladus provides valuable insights into the processes that can create and sustain potentially habitable environments beyond Earth. These moons highlight the diversity of planetary bodies in our solar system and the various conditions under which life might arise. The exploration of these moons continues to inspire and challenge scientists, pushing the boundaries of our understanding and technological capabilities. Titan and Enceladus represent some of the most exciting frontiers in planetary science and the search for life beyond our planet. Saturn's magnetic field is generated by the movement of metallic hydrogen within its interior. This field is slightly weaker than Jupiter's, but still much stronger than Earth's. The magnetic field creates a magnetosphere that extends millions of kilometers into space, protecting the planet from the solar wind and cosmic radiation. Saturn's magnetosphere is filled with charged particles, mostly originating from its moon Enceladus, where geysers eject water vapor and ice into space. These particles are trapped by Saturn's magnetic field, forming radiation belts similar to those found around Earth and Jupiter. The interaction between the magnetosphere and the solar wind creates stunning auroras at Saturn's poles, similar to the northern and southern lights on Earth. Saturn's auroras are influenced by both the solar wind and the planet's rapid rotation. The rotation generates strong electric currents that drive the auroras. The Cassini spacecraft provided detailed observations of Saturn's auroras, capturing images in ultraviolet light that revealed their complex and dynamic nature. These auroras can appear as glowing ovals around the poles, or as swirling patterns that change rapidly, indicating the highly dynamic interactions within Saturn's magnetosphere. The auroras on Saturn are also influenced by the planet's rings, which can block charged particles and create gaps in the auroral patterns. The magnetic field of Saturn is aligned closely with its rotation axis, which is unusual compared to other planets where the magnetic field is often tilted. This alignment results in a more symmetrical magnetosphere, but the field still exhibits variations and complexities due to the interactions with the solar wind and the moons. The study of Saturn's magnetic field provides insights into the planet's internal structure and the processes that generate magnetic fields in gas giants. Understanding Saturn's magnetosphere also helps scientists learn more about space weather and the behavior of magnetic fields and charged particles in other planetary systems. The exploration of Saturn's auroras and magnetic field continues to reveal the dynamic nature of the planet's atmosphere and space environment. These studies not only enhance our knowledge of Saturn, but also contribute to our understanding of magnetic fields and auroral phenomena throughout the universe. Space missions to Saturn have vastly expanded our knowledge of the planet, its rings, and its moons. The first mission to fly by Saturn was Pioneer 11, launched by NASA in 1973. It provided the first close-up images and data on Saturn's atmosphere and magnetic field. Following Pioneer 11, the Voyager 1 and Voyager 2 spacecraft conducted flybys of Saturn in 1980 and 1981, respectively. These missions revealed intricate details about Saturn's rings, discovered new moons, and provided detailed images of Titan's thick atmosphere. One of the most significant missions to Saturn was Cassini, a joint project between NASA, ESA, and ASI. Launched in 1997, Cassini arrived at Saturn in 2004 and spent 13 years studying the planet, its rings, and its moons in unprecedented detail. Cassini's findings transformed our understanding of Saturn. It provided stunning images and comprehensive data on the structure and composition of the rings, revealing complex interactions between ring particles and Saturn's moons. The Huygens probe, carried by Cassini, landed on Triton in 2005, providing the first direct exploration of this moon's surface. Huygens sent back images and data revealing a landscape shaped by liquid methane and ethane, similar to Earth's rivers and lakes. Cassini discovered water ice geysers on Enceladus, suggesting a subsurface ocean beneath the moon's icy crust. This finding raised the possibility of habitable environments beyond Earth, making Enceladus a prime target for future exploration. Cassini also observed seasonal changes on Saturn and Triton, providing insights into the atmospheric dynamics and climatic patterns of these distant worlds. The mission's long duration allowed scientists to study how these changes unfold over time. The mission detected the presence of complex organic molecules in the plumes of Enceladus, indicating that the Moon's subsurface ocean contains the building blocks of life. This discovery has significant implications for the search for extraterrestrial life. Cassini's close flybys of Saturn's rings revealed the presence of propeller-shaped structures caused by small moonlets embedded within the rings. These structures provide insights into the processes of moon formation and ring dynamics. The spacecraft also discovered that Saturn's moon Iapetus has a distinctive two-tone coloration, with one hemisphere much darker than the other. This unique feature sparked interest in the geological and surface processes on Iapetus. Cassini provided detailed maps of Saturn's magnetosphere, showing how it interacts with the solar wind and the planet's moons. These observations helped scientists understand the dynamics of Saturn's magnetic field and its impact on the surrounding space environment. In its grand finale, Cassini performed daring dives between Saturn and its rings, providing unprecedented close-up data on the planet's atmosphere and inner rings. These final orbits offered unique insights into the gravitational interactions and composition of the rings. Future missions to Saturn are being planned to build on Cassini's legacy. Proposed missions like the Dragonfly drone to Titan aim to explore the Moon's surface and atmosphere in greater detail, searching for signs of prebiotic chemistry and habitability. Another proposed mission is Enceladus Life Finder, which would focus on analyzing the plumes of Enceladus for signs of microbial life, further investigating the Moon's subsurface ocean and its potential to support life. The exploration of Saturn and its moons continues to inspire and challenge scientists. Each mission uncovers new mysteries and deepens our understanding of the solar system, driving the quest for knowledge about the origins and nature of planetary systems and the potential for life beyond Earth. Uranus stands out in the solar system due to its unique axial tilt. The planet is tilted at an angle of about 98 degrees, meaning it essentially orbits the Sun on its side. This extreme tilt leads to unusual seasonal variations, with each pole getting around 42 years of continuous sunlight, followed by 42 years of darkness. The cause of Uranus's extreme tilt is believed to be a result of a colossal collision with an Earth-sized object early in the planet's history. This impact likely knocked Uranus onto its side, setting it apart from the other planets. Uranus's rotation period is approximately 17 hours and 14 minutes. Despite its extreme axial tilt, the planet rotates in a prograde direction, which is the same direction as most planets in the solar system. The tilted axis means that Uranus experiences extreme seasonal changes. During its 84-year orbit around the Sun, each pole spends about 42 years in continuous daylight and then 42 years in darkness, leading to dramatic variations in temperature and atmospheric conditions. This unique tilt affects the planet's weather patterns. The sunlight hitting the polar regions can cause significant heating, while the equatorial region experiences more stable conditions. These differences create complex atmospheric dynamics. Uranus's unusual orientation also influences its magnetic field. Unlike other planets, the magnetic field is not aligned with its rotational axis and is significantly tilted. It's also offset from the planet's center, creating a complex and dynamic magnetosphere. The magnetic field is likely generated by motion within a layer of electrically conductive water and ammonia. This unconventional magnetic field contributes to irregular auroras and unique interactions with the solar wind. The planet's moons and rings orbit in the same tilted plane, perpendicular to the ecliptic plane of the solar system. This alignment adds to the distinctiveness of Uranus's celestial mechanics. Observations of Uranus's atmosphere reveal subtle banding and storm activity, though these features are more subdued compared to the atmospheres of Jupiter and Saturn. The planet's pale blue color is due to the presence of methane in its atmosphere, which absorbs red light. Voyager 2, the only spacecraft to visit Uranus, provided crucial data on its tilt and rotation during its flyby in 1986. The spacecraft's observations helped scientists understand the planet's unique characteristics and the effects of its axial tilt. The extreme seasons result in variations in cloud cover and atmospheric temperature. Studies have shown that the southern hemisphere, currently experiencing winter, is colder and has fewer visible clouds compared to the more active northern hemisphere. The peculiar rotation of Uranus also affects its wind patterns. Wind speeds can reach up to 900 kilometers per hour, and these winds flow in a retrograde direction near the equator and prograde at higher latitudes, showing complex atmospheric circulation. The tilted magnetic field creates a highly irregular magnetosphere that wobbles as the planet rotates. This wobbling leads to varying exposure of the magnetic poles to the solar wind, resulting in fluctuating magnetospheric activity. Future missions to Uranus aim to investigate its tilt and rotation more thoroughly. Understanding these unique aspects could provide insights into planetary formation and the dynamics of celestial bodies with extreme axial tilts. The study of Uranus's tilt and rotation not only highlights the planet's uniqueness, but also broadens our knowledge of the diverse characteristics that planets can exhibit. It challenges our understanding of planetary science and inspires further exploration of the outer solar system. Uranus's atmosphere is primarily composed of hydrogen and helium, with a significant amount of methane. The methane gives the planet its distinctive blue-green color by absorbing red light from the sun and reflecting blue light. The upper atmosphere contains traces of water, ammonia, and other hydrocarbons. These elements contribute to the formation of clouds and hazes, although they are not as visually prominent as those on Jupiter or Saturn. Uranus has the coldest planetary atmosphere in the solar system, with temperatures dropping as low as -224 degrees Celsius. This extreme cold is due to the planet's great distance from the sun and its lack of an internal heat source. The atmosphere is divided into layers, including the troposphere, stratosphere, and thermosphere. The troposphere is where weather occurs, and it extends from the planet's surface up to about 50 kilometers. In the troposphere, the temperature decreases with altitude, reaching a minimum at the tropopause. Above this, in the stratosphere, the temperature increases due to the absorption of ultraviolet radiation by methane and other gases. Clouds in Uranus's atmosphere are made up of various substances, including methane, ammonia, and water. The cloud tops are composed mainly of methane ice, while deeper clouds contain ammonia and water ice. Uranus's weather patterns are driven by its axial tilt and the small amount of sunlight it receives. The extreme tilt causes unusual seasonal variations, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Despite the low levels of solar energy, Uranus exhibits strong winds and occasional storms. Wind speeds can reach up to 900 kilometers per hour, particularly around the equator and in the mid-latitudes. These winds create banded patterns in the atmosphere, although they are less distinct than those on Jupiter and Saturn. The bands are regions of alternating wind directions, contributing to the planet's dynamic weather system. Seasonal changes on Uranus result in variations in cloud cover and atmospheric activity. During the summer and winter solstices, one hemisphere is bathed in continuous sunlight, affecting the temperature and cloud formation patterns. Observations by the Hubble Space Telescope and other instruments have detected large storm systems on Uranus. These storms can be bright spots in the atmosphere, indicating intense atmospheric activity. The storms on Uranus are less frequent and less violent than those on the other gas giants, but they still provide valuable insights into the planet's atmospheric dynamics and energy balance. The lack of a significant internal heat source means that most of the atmospheric activity on Uranus is driven by external solar energy. This makes Uranus's weather patterns unique compared to the other gas giants, which have strong internal heat sources. The study of Uranus's atmosphere and weather patterns helps scientists understand the range of climatic conditions possible on gas giants. It also provides a comparative basis for studying exoplanets with similar compositions and distances from their stars. Future missions to Uranus, equipped with advanced atmospheric probes and imaging technology, could reveal more about the complex interactions and processes that govern the planet's atmosphere. This knowledge would further our understanding of planetary atmospheres and the factors that influence their weather patterns. Uranus has a complex system of moons and rings that add to its unique charm. The planet has 27 known moons, each with its own distinct characteristics and features. The largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda, the innermost of the 5 major moons, has one of the most varied and extreme landscapes in the solar system. Its surface is a patchwork of canyons, ridges, and broken terrain, suggesting a history of intense geological activity. Ariel is one of the brightest of Uranus's moons and appears to have the youngest surface, marked by fewer craters and extensive fault systems. These features suggest that Ariel has experienced significant tectonic and possibly cryovolcanic activity. Umbriel, in contrast, is the darkest of the large moons. It has a heavily cratered surface with large, dark regions, indicating that it has remained relatively unchanged for billions of years. Its surface is less reflective, hinting at a composition of dark, carbon-rich material. Titania is the largest moon of Uranus and has a complex surface with fault valleys and canyons. The presence of these features indicates tectonic activity, likely driven by the moon's cooling and contraction over time. Oberon, the outermost of the 5 major moons, has a surface marked by large impact craters and a network of chasmata, or canyons. These features suggest a history of significant geological activity, though it appears to be less active today. Uranus's moons are thought to be composed primarily of water ice, mixed with rock and possibly organic compounds. The diverse surfaces and geological features of these moons provide valuable insights into the processes that shape icy bodies in the outer solar system. In addition to its moons, Uranus has a faint ring system composed of dark, narrow rings. There are 13 known rings, with the brightest being the Epsilon ring. These rings are much darker and less extensive than those of Saturn. The rings of Uranus are composed mainly of large particles, ranging from centimeters to meters in size. They are thought to be made of water ice with a dark coating of radiation-processed organic material. The rings are very narrow, typically only a few kilometers wide. This narrowness is likely due to the gravitational influence of nearby moons, known as shepherd moons, which help confine the ring particles and maintain their structure. The rings were first discovered in 1977 when astronomers observed the occultation of a star by Uranus and noticed multiple dips in the star's brightness. This discovery was unexpected and revealed the presence of the ring system. Voyager 2 provided detailed images of the rings during its flyby in 1986, showing their structure and composition. The spacecraft's observations confirmed the existence of shepherd moons and provided the first close-up views of the ring system. The origins of Uranus's rings and moons remain a topic of research. They could have formed from the debris of past collisions or from the remnants of the original material that formed Uranus. Understanding their formation provides clues about the history of the outer solar system. Future missions to Uranus aim to study its rings and moons in greater detail. Advanced imaging and spectroscopy could reveal more about the composition, structure, and dynamics of these intriguing features. The study of Uranus's moons and rings not only enhances our knowledge of the planet itself, but also contributes to our understanding of the formation and evolution of planetary systems. These insights are essential for piecing together the complex history of our solar system. Exploration of Uranus has been limited but highly valuable. The only spacecraft to visit Uranus was Voyager 2, which flew by the planet in 1986. This brief encounter provided a wealth of data on Uranus's atmosphere, moons, rings, and magnetosphere. Voyager 2's flyby revealed many details about Uranus's 5 major moons and discovered 10 additional moons. The spacecraft's images showed the diverse and complex surfaces of these moons, hinting at geological activity and varied histories. The mission also provided the first detailed images of Uranus's rings, revealing their narrow and dark nature. Voyager 2's observations confirmed the existence of shepherd moons, which help maintain the structure of the rings. Voyager 2 measured the planet's magnetic field and discovered that it is tilted relative to Uranus's rotation axis. This tilt causes the magnetosphere to wobble as the planet rotates, leading to unique interactions with the solar wind. The spacecraft's instruments detected strong winds in Uranus's atmosphere, with speeds reaching up to 900 kilometers per hour. These winds create banded patterns and drive the planet's weather systems. Following the Voyager 2 flyby, Uranus has been observed primarily by ground-based telescopes and space telescopes such as the Hubble Space Telescope. These observations have continued to provide valuable data on the planet and its moons. The Hubble Space Telescope has captured images of Uranus's atmosphere, showing seasonal changes and the appearance of large storm systems. These observations help scientists understand the dynamics of the planet's weather. Ground-based telescopes have also observed Uranus's rings, monitoring their structure and variations over time. These observations contribute to our understanding of the processes that shape and maintain the rings. Advances in technology have allowed for more detailed observations of Uranus from Earth. Adaptive optic systems on ground-based telescopes have improved the resolution of images, revealing finer details of the planet and its moons. Proposals for future missions to Uranus have been made, emphasizing the need for an orbiter to study the planet in greater detail. Such a mission could provide comprehensive data on Uranus's atmosphere, interior, magnetosphere, rings, and moons. A dedicated Uranus orbiter could also carry instruments to study the planet's magnetic field and its interactions with the solar wind. Understanding these interactions is crucial for learning more about the planet's magnetosphere and space environment. Exploring Uranus's moons in greater detail is another priority for future missions. Instruments could analyze the surface composition, geological features, and potential subsurface oceans, particularly on Miranda, Ariel, and Titania. The potential for a flyby mission or a lander to one of Uranus's moons could provide direct analysis of surface materials and insights into the geological processes that have shaped these moons. Continued observations from telescopes and potential future missions will enhance our understanding of Uranus and its place in the solar system. Each new discovery builds on the legacy of Voyager 2 and the valuable data it provided. The exploration and observation of Uranus remain a fascinating and important field of study. As technology advances and our capabilities grow, the secrets of this distant and unique planet will continue to be unveiled, enriching our knowledge of the solar system and the universe. The potential for future missions to Uranus is a topic of great interest among planetary scientists. With the success of missions to Jupiter and Saturn, there is a strong case for a dedicated mission to Uranus to explore its unique characteristics in detail. One of the primary goals for a future Uranus mission would be to send an orbiter. An orbiter could conduct long-term studies of the planet's atmosphere, rings, moons, and magnetosphere, providing continuous and detailed data. The proposed Uranus orbiter and probe mission aims to achieve this. It would include a main orbiter and an atmospheric probe. The probe would descend into Uranus's atmosphere, measuring its composition and structure in situ. Understanding Uranus's internal structure is another key objective. The orbiter could use gravity field measurements to infer details about the planet's core and the distribution of materials within its interior. A future mission could also investigate Uranus's extreme axial tilt and its impact on the planet's atmospheric dynamics and seasonal variations. This information would help scientists understand how such a tilt influences weather and climate. Studying Uranus's magnetic field is crucial as well. A dedicated mission could map the magnetic field in high resolution, revealing its origin and how it interacts with the solar wind and the planet's moons. Uranus's moons present another exciting opportunity for exploration. A mission could conduct close flybys of the major moons, capturing high-resolution images and collecting data on their surface composition and geological history. The potential for subsurface oceans on some of Uranus's moons, like Miranda and Ariel, is particularly intriguing. Instruments could search for signs of liquid water beneath the icy crusts, which might hint at the potential for life. A lander or rover could be considered for one of Uranus's moons. Such a mission would allow for direct analysis of the surface materials, providing unprecedented insights into the moon's composition and geological processes. Exploring Uranus's rings would also be a priority. Detailed studies of the ring's structure, particle size distribution, and composition could shed light on their origin and the processes that sustain them. A mission could include a suite of instruments designed to study the interactions between the rings and the moons, as well as the impact of the planet's magnetic field on these interactions. International collaboration could enhance the scope and capabilities of a Uranus mission. By pooling resources and expertise, space agencies around the world could undertake a more comprehensive and ambitious exploration of Uranus. The timeline for such a mission would likely extend over the next few decades. Launch windows to Uranus are infrequent due to its distance, and mission durations would be long, requiring years of travel time. Continued advancements in spacecraft technology and instrumentation will be essential for the success of a Uranus mission. Innovations in power generation, propulsion, and data transmission will enable more sophisticated and capable missions. The potential for future missions to Uranus holds great promise for expanding our understanding of the outer solar system. By exploring this distant and enigmatic planet, we will gain new insights into the diversity and complexity of planetary systems, enriching our knowledge of the universe. Neptune's atmosphere is composed mainly of hydrogen and helium, with a significant amount of methane. The methane gives Neptune its striking blue color by absorbing red light and reflecting blue light. The atmosphere is divided into several layers, including the troposphere, stratosphere, thermosphere, and exosphere. The troposphere is where most of the weather phenomena occur, extending up to about 50 kilometers above the planet's surface. Neptune's atmosphere is known for its dynamic weather patterns and extreme winds. The planet has some of the fastest winds in the solar system, reaching speeds of up to 2,100 kilometers per hour. These high-speed winds create prominent cloud bands and storm systems that are visible in the atmosphere. The clouds are made up of methane ice crystals, which give them a bright, white appearance against the blue background. One of the most famous features in Neptune's atmosphere is the Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot. The Great Dark Spot was first observed by the Voyager 2 spacecraft in 1989. The Great Dark Spot is a high-pressure system with winds swirling around its center. It was roughly the size of Earth when first discovered, but it has since disappeared, showcasing the transient nature of Neptune's atmospheric storms. Neptune also exhibits other dark spots and bright clouds that appear and disappear over time. These features indicate a highly dynamic and ever-changing atmosphere, with new storms forming and dissipating regularly. The planet's rapid rotation, with a day lasting about 16 hours, contributes to the formation of strong jet streams. These jet streams separate different atmospheric bands, creating the distinct striped appearance seen in images of Neptune. Neptune's atmosphere also experiences significant seasonal changes due to its axial tilt of about 28 degrees. As the planet orbits the Sun over its 165-year period, different parts of the atmosphere are exposed to varying amounts of sunlight, driving seasonal variations. In addition to large storm systems, Neptune's atmosphere hosts smaller, high-altitude clouds known as scooters. These clouds move rapidly around the planet and are thought to be composed of frozen methane. The upper atmosphere of Neptune contains a hazy layer of hydrocarbons formed by the interaction of methane with ultraviolet radiation from the Sun. This haze contributes to the overall appearance and coloration of the planet. Neptune's temperature varies significantly between different atmospheric layers. The troposphere is relatively warmer due to heat generated from the planet's interior, while the stratosphere and thermosphere are colder due to lower pressure and less sunlight. The internal heat of Neptune plays a crucial role in driving its weather phenomena. The planet radiates more heat than it receives from the Sun, suggesting an active internal heat source that influences atmospheric dynamics. Observations from telescopes and spacecraft continue to reveal new details about Neptune's atmosphere and weather. The Hubble Space Telescope has provided high-resolution images, capturing changes in storm activity and cloud formations over time. Understanding Neptune's atmosphere and weather phenomena helps scientists learn more about the dynamics of gas giant planets, both in our solar system and around other stars. The study of Neptune's atmosphere provides valuable insights into the processes that govern planetary atmospheres and the complexities of weather on distant worlds. Triton is the largest moon of Neptune and one of the most intriguing objects in the solar system. It was discovered by British astronomer William Lassell just 17 days after Neptune itself was discovered in 1846. Triton is unique among large moons because it orbits Neptune in a retrograde direction, meaning it moves in the opposite direction to Neptune's rotation. This unusual orbit suggests that Triton may have been captured by Neptune's gravity and was not originally formed in orbit around the planet. The surface of Triton is extremely cold, with temperatures around -235 degrees Celsius. This makes it one of the coldest objects in the solar system. Despite these frigid temperatures, Triton exhibits a variety of interesting geological features. Triton's surface is a mix of smooth plains, rugged terrain, and large ice volcanoes, also known as cryovolcanoes. These cryovolcanoes are believed to erupt with liquid water, ammonia, or methane, which then freezes and falls back to the surface. Voyager 2, the only spacecraft to visit Neptune and Triton, provided detailed images and data during its flyby in 1989. The spacecraft revealed a surface covered with nitrogen ice, methane ice, and water ice, along with dark streaks that suggest active geysers or plumes. One of the most striking features of Triton's surface is the presence of cantaloupe terrain, named for its resemblance to the skin of a cantaloupe melon. This region is characterized by a pattern of ridges and depressions and indicates a history of significant geological activity. Triton's thin atmosphere is primarily composed of nitrogen, with traces of methane. The atmosphere is so thin that it exerts very little pressure on the surface, similar to the conditions on Mars. Seasonal changes on Triton cause the surface ice to sublimate or turn directly from solid to gas during the southern summer. This process creates a thin layer of nitrogen gas that temporarily thickens the atmosphere. Triton has a relatively young surface with few impact craters. This suggests that the Moon has been geologically active relatively recently, reshaping its surface and erasing older features. The retrograde orbit and geological activity of Triton suggests that it might have once been a dwarf planet in the Kuiper Belt before being captured by Neptune's gravity. This capture would have generated significant tidal forces, heating Triton's interior and driving its geological activity. Triton's geysers and plumes, which eject material up to 8 kilometers high, are driven by seasonal heating and are primarily composed of nitrogen gas and dust particles. These plumes provide direct evidence of ongoing surface processes. The exploration of Triton has been limited to the Voyager 2 flyby, but future missions could provide more detailed information. Proposals for orbiters or landers aim to study Triton's geology, atmosphere, and potential subsurface ocean in greater depth. Understanding Triton's unique characteristics and history helps scientists learn more about the processes that shape icy moons and the interactions between moons and their parent planets. The study of Triton also provides insights into the broader population of Kuiper Belt objects and the dynamics of planetary capture. This information is crucial for understanding the formation and evolution of the outer solar system. Triton remains one of the most fascinating targets for future exploration, with its dynamic surface, thin atmosphere, and potential for an internal ocean offering a wealth of scientific opportunities. The mysteries of Triton continue to inspire curiosity and the desire for further discovery. Neptune has a faint and complex ring system composed primarily of dust particles and small ice particles. The rings were first confirmed by the Voyager 2 spacecraft during its flyby in 1989. The rings are named after astronomers who made significant contributions to the study of Neptune: Gali, Leverrier, Lassell, Arago, and Adams. Each ring varies in width, density, and particle composition. Unlike the bright and broad rings of Saturn, Neptune's rings are dark and narrow. This suggests that they are composed of a mixture of water ice and radiation-processed organic material, which gives them a reddish hue. The Adams ring, the outermost ring, is particularly interesting because it contains 3 prominent arcs named Liberty, Equality, and Fraternity. These arcs are regions where the ring material is more densely packed than in other parts of the ring. The presence of these arcs puzzled scientists for many years, as they seemed to defy the expectations of ring dynamics. It is now believed that the gravitational influence of Neptune's moon Galatea helps maintain the structure of the arcs. The particles in Neptune's rings are thought to range in size from tiny dust grains to small boulders. The narrowness of the rings suggests that the particles are confined by the gravitational influence of nearby moons, known as shepherd moons. Voyager 2's observations revealed that Neptune's rings are not uniform. They contain clumps and density waves indicating ongoing interactions between the ring particles and Neptune's moons. The Gal ring is the innermost ring and is very faint. It is followed by the Leverrier ring, which is narrow and contains more material than the Gal ring. The Lassell and Arago rings are broad and diffuse, adding to the complexity of Neptune's ring system. The ring system's composition and structure suggest that they may be relatively young and possibly formed from the debris of a shattered moon or comet. Collisions between small moons or the disruption of a larger moon could have generated the ring material. Dust from micrometeoroid impacts on Neptune's moons might also contribute to the rings. These impacts can eject particles into space, where they become part of the ring system. The study of Neptune's rings provides valuable insights into the processes that govern ring formation and evolution. By comparing Neptune's rings to those of other giant planets, scientists can better understand the dynamics of ring systems in the solar system. Future missions to Neptune could offer more detailed observations of the rings. Advanced imaging and spectroscopy could reveal more about their composition, structure, and interactions with Neptune's moons. Ground-based observations and the Hubble Space Telescope continue to monitor Neptune's rings, but the faintness and distance make detailed study challenging. Spacecraft missions would provide the clarity and resolution needed for deeper understanding. The unique characteristics of Neptune's rings, such as the arcs in the Adam's ring, highlight the complexity and diversity of planetary ring systems. These features continue to intrigue and challenge scientists, prompting further study. Understanding Neptune's rings not only sheds light on the history and dynamics of this distant planet, but also enhances our knowledge of the formation and evolution of ring systems around other planets and celestial bodies in our universe. The discovery of Neptune was a significant event in the history of astronomy. It was the first planet found through mathematical predictions rather than direct observation. In the early 19th century, discrepancies in Uranus's orbit suggested the presence of another distant planet exerting gravitational influence. In 1845, French astronomer Urbain Le Verrier and British mathematician John Couch Adams independently calculated the position of this unknown planet. Their predictions led to the successful observation of Neptune on September 23, 1846, by German astronomer Johann Galle at the Berlin Observatory. Neptune's discovery confirmed the power of Newtonian mechanics and marked a triumph for theoretical astronomy. The planet was named after the Roman god of the sea, in keeping with the naming convention for planets. Early observations of Neptune were limited to telescopic studies from Earth. These observations revealed its bluish color and a few faint moons, but detailed information about the planet remained elusive until the advent of space exploration. The Voyager 2 spacecraft, launched by NASA in 1977, became the first and only mission to visit Neptune. It flew by the planet on August 25, 1989, providing humanity with its first close-up images and comprehensive data about Neptune and its moons. Voyager 2's flyby revealed a dynamic and active planet with strong winds, large storm systems, and a complex magnetic field. The spacecraft also discovered 6 new moons and provided detailed images of Triton, Neptune's largest moon. One of the most remarkable discoveries was the Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot. This dark, oval-shaped storm highlighted the turbulent nature of Neptune's atmosphere. The spacecraft also provided the first detailed images of Neptune's ring system, revealing its faint and narrow rings with embedded arcs. These findings deepened our understanding of the planet's gravitational interactions and ring dynamics. Voyager 2's observations of Triton revealed a geologically active moon with a surface covered in nitrogen ice, geysers ejecting nitrogen gas, and a retrograde orbit, suggesting it was a captured Kuiper Belt object. Following Voyager 2, Neptune has been studied primarily through ground-based telescopes and the Hubble Space Telescope. These observations have continued to monitor atmospheric changes, storms, and seasonal variations. Hubble's observations have captured images of Neptune's dynamic weather, including the formation and dissipation of dark spots and bright clouds. These ongoing studies help scientists track atmospheric phenomena over time. Despite the wealth of data provided by Voyager 2 and telescopic observations, many questions about Neptune remain unanswered. The planet's internal structure, the full extent of its atmospheric dynamics, and detailed characteristics of its moons and rings are areas ripe for further exploration. The scientific community has proposed several mission concepts to return to Neptune. These include orbiters, atmospheric probes, and flybys designed to gather comprehensive data on the planet and its moons. One such proposal is the Neptune Odyssey mission, which aims to place an orbiter around Neptune to conduct long-term studies of its atmosphere, magnetic field, and moons. This mission could provide insights into Neptune's formation and evolution. Future exploration of Neptune promises to expand our knowledge of the outer solar system and the processes that shape giant planets. By studying Neptune in greater detail, scientists hope to uncover the mysteries of this distant, enigmatic world and its place in the broader context of planetary science. The discovery and exploration history of Neptune underscores the importance of both theoretical predictions and direct observation in advancing our understanding of the cosmos. It highlights the continual drive to explore and learn about the farthest reaches of our solar system. Future exploration prospects for Neptune are incredibly exciting, as new missions could unlock many of the planet's mysteries. Scientists are advocating for a dedicated mission to study Neptune and its moons in greater detail. One of the most ambitious proposals is the Neptune Odyssey mission, which aims to send an orbiter to Neptune. This mission would provide long-term observations of the planet's atmosphere, rings, and moons, offering unprecedented insights. An orbiter would be equipped with advanced instruments to study Neptune's magnetic field, atmospheric composition, and weather patterns. Such a mission could also map the planet's gravitational field to learn more about its internal structure. The study of Neptune's dynamic atmosphere is a key objective for future missions. Scientists hope to understand the mechanisms driving the planet's extreme winds and storms, as well as the seasonal changes observed in its atmosphere. Exploring Neptune's rings is another priority. Future missions could use high-resolution cameras and spectrometers to analyze the composition and structure of the rings, as well as the forces that shape them. Triton, Neptune's largest moon, is a particularly intriguing target. Its retrograde orbit and active geology make it an excellent candidate for detailed exploration. A lander or probe could study its surface and geysers, searching for signs of a subsurface ocean. There is significant interest in sending a probe into Neptune's atmosphere. This probe would descend through the planet's clouds, measuring temperature, pressure, and chemical composition, providing valuable data about the planet's weather and climate. International collaboration could enhance the scope of a Neptune mission. By combining resources and expertise, space agencies could undertake a more comprehensive exploration, much like the successful Cassini-Huygens mission to Saturn and Triton. The development of new propulsion technologies, such as solar electric propulsion or nuclear thermal propulsion, could make a mission to Neptune more feasible. These technologies would enable faster travel times and longer mission durations. Continued advancements in robotics and artificial intelligence will also play a crucial role. Autonomous systems will be essential for operating in the harsh and distant environment of Neptune, allowing for more sophisticated scientific experiments. Public interest and support are vital for the success of future Neptune missions. Engaging the public through educational programs and outreach can help generate enthusiasm and funding for these ambitious projects. The potential for discovering new moons or even capturing detailed images of distant objects in the Kuiper Belt adds to the allure of Neptune exploration. Every new piece of data could significantly advance our understanding of the outer solar system. A successful mission to Neptune would not only provide answers to long-standing questions, but also inspire future generations of scientists and engineers. The technological and scientific advancements from such a mission could have far-reaching impacts. Future missions to Neptune will build on the legacy of Voyager 2, leveraging modern technology to delve deeper into the planet's secrets. These missions will continue the tradition of exploration that has driven humanity to reach for the stars. The exploration of Neptune stands as a testament to human curiosity and the desire to understand our place in the cosmos. As we look to the future, the prospect of uncovering the mysteries of this distant world offers a thrilling journey of discovery. Dwarf planets are celestial bodies that orbit the Sun and share some characteristics with the larger planets, but they do not dominate their orbits. They are smaller than the major planets, but larger than typical asteroids. The International Astronomical Union, IAU, defines a dwarf planet as an object that orbits the Sun, has sufficient mass to assume a nearly round shape, has not cleared its orbital path of other debris, and is not a satellite. One of the most well-known dwarf planets is Pluto. Once considered the 9th planet of the solar system, Pluto was reclassified as a dwarf planet in 2006 after the IAU formalized the definition. Pluto has a diameter of about 2,377 kilometers, making it the largest known dwarf planet in the solar system. It has a thin atmosphere composed primarily of nitrogen with traces of methane and carbon monoxide. Eris is another significant dwarf planet, slightly smaller than Pluto. Discovered in 2005, Eris has a highly elliptical orbit and takes about 558 years to complete one revolution around the Sun. Eris's discovery was one of the key factors that led to the reclassification of Pluto. Its presence showed that there were other similar-sized objects in the solar system that needed to be categorized. Haumea is a dwarf planet known for its elongated shape, which results from its rapid rotation. Haumea's day lasts only about 4 hours, causing it to become elongated. It also has 2 known moons. Makemake is another dwarf planet, slightly smaller than Pluto. It was discovered in 2005 and has a bright surface covered with methane ice. Unlike Pluto, Makemake does not have a significant atmosphere. Ceres is the closest dwarf planet to the Sun, located in the asteroid belt between Mars and Jupiter. It was the first dwarf planet to be visited by a spacecraft, with NASA's Dawn mission providing detailed images and data. Ceres has a diameter of about 940 kilometers and shows evidence of water ice beneath its surface. Its surface is marked by large craters and mysterious bright spots, thought to be deposits of salt. The characteristics of dwarf planets provide valuable insights into the formation and evolution of the solar system. Their diverse properties and locations offer clues about the processes that shaped the early solar system. Unlike the major planets, dwarf planets have not cleared their orbits of other debris. This characteristic highlights the different evolutionary paths taken by these small bodies compared to their larger counterparts. Studying dwarf planets can also shed light on the potential for similar objects in other planetary systems. Understanding their composition, geology, and atmospheres helps scientists develop models of planetary formation and dynamics. The exploration of dwarf planets is still in its early stages, but missions like New Horizons, which visited Pluto, and Dawn, which studied Ceres, have provided a wealth of information. Future missions may target other dwarf planets, revealing more about these intriguing objects. As our knowledge of the solar system grows, the study of dwarf planets continues to be a vital part of understanding the diversity and complexity of planetary bodies that orbit our Sun. These small worlds hold many secrets that are waiting to be uncovered. Pluto was discovered in 1930 by astronomer Clyde Tombaugh at the Lowell Observatory in Arizona. For 76 years, Pluto was considered the ninth planet of the solar system. Pluto is located in the Kuiper Belt, a region of the solar system beyond Neptune that is populated with small icy bodies and dwarf planets. It takes about 248 Earth years for Pluto to complete one orbit around the Sun. Pluto's orbit is highly elliptical, and at times it is closer to the Sun than Neptune. Despite this, there is no danger of collision due to the two bodies' orbital resonance, which ensures they remain in stable positions relative to each other. In 2006, the International Astronomical Union, IAU, redefined the criteria for what constitutes a planet. According to this new definition, a planet must orbit the Sun, be spherical in shape, and have cleared its orbit of other debris. Pluto meets the first two criteria, but does not meet the third. Its orbit is shared with other objects in the Kuiper Belt, and thus it was reclassified as a dwarf planet. The reclassification of Pluto was controversial and sparked much debate among scientists and the general public. Many people felt an emotional attachment to Pluto's status as the ninth planet and were disappointed by the change. Despite its reclassification, Pluto remains an object of great interest and study. It has 5 known moons, with Charon being the largest. Charon is so large compared to Pluto that the two are often referred to as a double dwarf planet system. The New Horizons mission, launched by NASA in 2006, provided the first close-up images and detailed data of Pluto and its moons when it flew by the dwarf planet in 2015. This mission revealed a diverse and complex world with a variety of geological features. New Horizons discovered that Pluto has a surprisingly active surface, with features such as mountains made of water ice, vast plains of nitrogen ice, and evidence of cryovolcanism. These findings suggest that Pluto has been geologically active in the recent past. One of the most striking features on Pluto's surface is the heart-shaped region known as Tombaugh Regio. This area is dominated by Sputnik Planitia, a vast, smooth plain of nitrogen ice that appears to be relatively young and free of impact craters. Pluto's atmosphere is primarily composed of nitrogen, with traces of methane and carbon monoxide. The atmosphere is thin and extends far into space, gradually escaping from Pluto's weak gravity. The reclassification of Pluto has led to a broader understanding and recognition of other dwarf planets in the solar system. Objects like Eris, Haumea, and Makemake are now studied alongside Pluto as part of this new category. The study of Pluto and its reclassification has contributed to our understanding of planetary science and the diversity of objects that orbit our Sun. It has also highlighted the dynamic nature of scientific classification and the importance of continuing exploration. Pluto's demotion from full planetary status has not diminished its significance in the field of astronomy. On the contrary, the interest and curiosity surrounding Pluto have only grown, driven by the fascinating discoveries made by New Horizons. The debate over Pluto's status has also emphasized the need for clear and consistent definitions in science, showing how new discoveries can challenge existing paradigms and lead to a deeper understanding of the universe. Eris is one of the most notable dwarf planets discovered in 2005 by a team led by Mike Brown at the Palomar Observatory. It is slightly smaller than Pluto, but more massive, which contributed to the debate over Pluto's planetary status. Eris has an extremely elliptical orbit that takes it far beyond the Kuiper Belt, into a region known as the scattered disk. It takes about 558 years for Eris to complete one orbit around the Sun. The surface of Eris is highly reflective, indicating it is covered with a layer of ice. Observations suggest that this ice is primarily composed of frozen methane, similar to the surface of Pluto. Eris has one known moon, Dysnomia. Studying Dysnomia's orbit has provided valuable information about Eris's mass and density, helping scientists understand more about its composition and structure. Haumea, another notable dwarf planet, was discovered in 2004 and is known for its unusual elongated shape. This shape is due to its rapid rotation, which causes it to stretch out into an ellipsoid. Haumea's day is only about 4 hours long, making it one of the fastest rotating large objects in the solar system. This rapid rotation is likely the result of a past collision with another object. Haumea has two known moons, Hi'iaka and Namaka. These moons are thought to have formed from debris ejected during the collision that gave Haumea its elongated shape. The surface of Haumea is covered in crystalline water ice, which is unusual because crystalline ice should not exist in the cold temperatures of the outer solar system. This suggests that Haumea may have experienced geological activity in the recent past. Makemake was discovered in 2005 and is slightly smaller than Pluto. It is one of the brightest objects in the Kuiper Belt due to its high albedo or reflectivity. Makemake has a surface covered with methane ice, similar to Pluto and Eris. Observations also suggest the presence of ethane and possibly nitrogen ice, indicating a complex surface composition. In 2016, a small moon was discovered orbiting Makemake. This discovery has provided new opportunities to study Makemake's mass and density, offering further insights into its characteristics. The discovery of Eris, Haumea, and Makemake has expanded our understanding of the diversity of objects in the Kuiper Belt. These dwarf planets share some similarities with Pluto, but also have unique features that set them apart. Studying these dwarf planets helps scientists learn more about the formation and evolution of the solar system. They provide clues about the processes that shaped the outer regions of the solar system and the variety of conditions that exist there. Future missions to these dwarf planets could reveal even more about their surfaces, atmospheres, and potential for geological activity. Advances in telescope technology will also allow for more detailed observations from Earth. The continued study of Eris, Haumea, Makemake, and other dwarf planets will enhance our knowledge of the Kuiper Belt and the broader context of planetary formation and evolution in our solar system. These distant worlds hold many secrets that are waiting to be uncovered. The Kuiper Belt is a vast region of the solar system that extends beyond the orbit of Neptune. It is populated with thousands of small icy bodies, including dwarf planets, comets, and other minor objects. This region was named after astronomer Gerard Kuiper, who theorized the existence of a belt of icy objects beyond Neptune in the 1950s. However, the first Kuiper Belt object, KBO, was not discovered until 1992. The Kuiper Belt is similar to the asteroid belt, but much larger. While the asteroid belt lies between Mars and Jupiter, the Kuiper Belt stretches from about 30 to 55 astronomical units, AU, from the Sun. One of the key characteristics of the Kuiper Belt is its diversity. It contains a wide variety of objects, from small icy rocks to large dwarf planets like Pluto, Haumea, Makemake, and Eris. The objects in the Kuiper Belt are thought to be remnants from the early solar system. They are relatively unchanged since their formation, making them valuable for studying the conditions and processes that existed over 4 billion years ago. The study of the Kuiper Belt helps scientists understand the distribution of small bodies in the solar system. It also provides insights into the dynamics of planetary orbits and the influence of giant planets like Neptune. Comets originate from the Kuiper Belt, specifically a region known as the scattered disk. These icy bodies are occasionally perturbed by gravitational interactions, sending them into the inner solar system as short-period comets. The Kuiper Belt plays a significant role in the theory of planetary migration. As the giant planets moved in their orbits, their gravitational interactions scattered many small bodies into the Kuiper Belt, influencing its current structure. Understanding the Kuiper Belt is crucial for piecing together the history of our solar system. It provides evidence of the migration of the giant planets and the early distribution of material in the protoplanetary disk. The discovery of the Kuiper Belt has expanded our knowledge of the outer solar system. Before its discovery, Pluto was considered an outlier. Now, it is understood as one of many similar objects in this distant region. The exploration of the Kuiper Belt is still in its early stages. The New Horizons mission, which flew by Pluto in 2015, continued on to visit another KBO, Arrokoth, in 2019, providing the first close-up images of a Kuiper Belt object beyond Pluto. These missions have revealed the complex geology and diverse surfaces of Kuiper Belt objects. Arrokoth, for example, showed a bilobed shape, suggesting a gentle collision between two objects in the early solar system. Future missions to the Kuiper Belt could provide more detailed studies of its objects. These missions would help answer fundamental questions about the composition, structure, and history of this distant region. The Kuiper Belt's significance extends beyond our solar system. Studying this region helps astronomers understand similar belts around other stars, known as debris disks, and the processes that shape planetary systems. The Kuiper Belt represents a frontier of exploration in our solar system. As technology advances and our understanding grows, the secrets of this distant region will continue to unfold, providing deeper insights into the origins and evolution of our cosmic neighborhood. Exploration missions to the outer solar system have provided some of the most exciting discoveries in space science. These missions have expanded our understanding of the giant planets, their moons, and the distant regions beyond. One of the earliest missions to the outer solar system was Pioneer 10, launched by NASA in 1972. It was the first spacecraft to travel through the asteroid belt and make a close flyby of Jupiter, sending back detailed images and data. Following Pioneer 10, Pioneer 11 was launched in 1973. This mission also flew by Jupiter and then continued on to Saturn, providing the first close-up images of Saturn and its rings. The Voyager missions, Voyager 1 and Voyager 2, launched in 1977, are among the most successful and celebrated missions to the outer solar system. Voyager 1 flew by Jupiter and Saturn, while Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune, providing a wealth of information about these planets and their moons. Voyager 1 is now the most distant human-made object, having entered interstellar space in 2012. Voyager 2 followed it into interstellar space in 2018. Both spacecraft continue to send back data, helping scientists learn about the boundary region of our solar system. The Galileo mission, launched in 1989, was the first spacecraft to orbit Jupiter. It provided detailed observations of Jupiter's atmosphere, magnetic field, and its moons, including the discovery of subsurface oceans on Europa and volcanic activity on Io. Cassini-Huygens, a joint mission of NASA, ESA, and ASI, launched in 1997, was one of the most ambitious missions to the outer solar system. Cassini orbited Saturn for over 13 years, studying the planet, its rings, and its moons, while the Huygens probe landed on Triton, providing the first direct observations of Titan's surface. The New Horizons mission, launched in 2006, made a historic flyby of Pluto in 2015, revealing a complex and active world. After Pluto, New Horizons continued on to the Kuiper Belt, flying by the object Arrokoth in 2019. Juno, launched in 2011, is currently studying Jupiter. Its mission is to understand the planet's origin and evolution by investigating its atmosphere, magnetic field, and gravitational field, providing insights into the deep interior of Jupiter. The exploration of the outer solar system has also included missions to comets and asteroids. The European Space Agency's Rosetta mission, for example, studied Comet 67P/Churyumov-Gerasimenko, providing valuable data on the composition and behavior of comets. Future missions are being planned to continue the exploration of the outer solar system. The Europa Clipper mission, set to launch in the 2020s, will conduct detailed reconnaissance of Jupiter's moon Europa, searching for signs of habitability and potential life in its subsurface ocean. Another proposed mission is the Dragonfly drone to Triton, which aims to explore the surface and atmosphere of Saturn's largest moon. Dragonfly will investigate Titan's organic chemistry and its potential to support life. The potential for a dedicated mission to Uranus or Neptune is also being discussed. Such a mission would provide long-term observations of these ice giants, their rings and their moons, significantly enhancing our understanding of these distant planets. Exploration missions to the outer solar system are incredibly challenging due to the vast distances and harsh environments. However, the scientific rewards are immense, offering insights into the origins and evolution of our solar system. These missions have transformed our understanding of the outer planets and their moons, revealing complex worlds with dynamic atmospheres, active geology, and the potential for subsurface oceans and life. The continued exploration of the outer solar system will push the boundaries of our knowledge, inspiring future generations of scientists and engineers. It represents a frontier of discovery that promises to reveal even more about our place in the universe. Upcoming missions and projects in space exploration are set to expand our understanding of the solar system and beyond. One of the most anticipated missions is NASA's Artemis program, which aims to return humans to the Moon by 2024 and establish a sustainable presence by 2028. The Artemis program includes the Gateway, a lunar orbiting outpost that will serve as a staging point for lunar landings and a hub for scientific research. This infrastructure will support future missions to Mars and other deep space destinations. NASA's Mars Sample Return mission, in collaboration with the European Space Agency, aims to collect samples from the Martian surface and bring them back to Earth for detailed analysis. This mission will build on the discoveries made by the Perseverance rover. The James Webb Space Telescope, set to launch soon, will be the most powerful space telescope ever built. It will explore the universe in infrared light, studying the formation of stars and galaxies and searching for signs of life on exoplanets. The Europa Clipper mission, planned for launch in the 2020s, will conduct detailed reconnaissance of Jupiter's moon Europa. It will investigate the moon's ice shell and subsurface ocean, searching for conditions that might support life. The Dragonfly mission to Titan, Saturn's largest moon, will launch in the mid-2020s. This rotorcraft will explore Titan's surface and atmosphere, studying its complex organic chemistry and assessing its habitability. NASA's Psyche mission, set to launch in 2022, will explore the metal-rich asteroid 16 Psyche. This mission aims to understand more about the building blocks of planet formation and the history of our solar system. China's space agency is planning a Mars sample return mission for the 2030s, following the success of its Tianwen-1 mission. This ambitious project aims to bring Martian samples back to Earth, complementing NASA's efforts. The European Space Agency's JUICE mission, launching in 2022, will study Jupiter's icy moons, Ganymede, Callisto, and Europa. This mission will investigate their potential for having subsurface oceans and their ability to support life. Russia is planning the Luna 25 mission to the Moon, which aims to explore the lunar South Pole and study its regolith. This mission is part of a broader plan to establish a long-term presence on the Moon. India's space agency ISRO is working on the Chandrayaan-3 mission, which will include a lunar lander and rover. This mission aims to further explore the lunar surface, following the success of Chandrayaan-2. Japan's Hayabusa 2 mission successfully returned samples from the asteroid Ryugu. Building on this success, Japan is planning the Martian moon's exploration mission to study and return samples from the moons of Mars. NASA's planned mission to Uranus and Neptune, still in the proposal stages, aims to explore these ice giants in greater detail. This mission would provide invaluable data on the composition, atmosphere, and magnetic fields of these distant planets. The search for exoplanets continues with missions like NASA's TESS and the European Space Agency's Pluto, which aim to discover and characterize planets around other stars. These missions will help identify potential habitable worlds. These upcoming missions and projects represent the next frontier in space exploration. They promise to deepen our understanding of the solar system, uncover new scientific insights, and inspire future generations to continue exploring the cosmos. The future of space exploration is bright, filled with potential for groundbreaking discoveries and the advancement of human knowledge. Technological advancements in space exploration have significantly enhanced our ability to explore the solar system and beyond. One of the most critical advancements is in propulsion technology, which enables faster and more efficient travel through space. Solar electric propulsion, for example, uses solar panels to generate electricity, which then powers ion thrusters. This technology allows for long-duration missions with a lower fuel mass, making it ideal for deep space exploration. Nuclear thermal propulsion is another promising technology. It uses nuclear reactions to heat a propellant, producing a powerful thrust. This method could significantly reduce travel time to distant destinations like Mars and the outer planets. Advances in robotics and artificial intelligence have also transformed space exploration. Autonomous rovers and landers can perform complex scientific tasks, navigate challenging terrains, and make real-time decisions without direct human intervention. The development of miniaturized instruments and sensors has enabled more comprehensive scientific investigations. These compact devices can be carried on smaller, more cost-effective missions, yet still provide detailed data on planetary environments. 3D printing technology is revolutionizing the construction and maintenance of spacecraft. Astronauts on the International Space Station have used 3D printers to create tools and replacement parts, reducing the need for resupply missions from Earth. In the realm of communications, laser-based systems are set to improve data transmission rates between Earth and distant spacecraft. These systems can send and receive large volumes of data much faster than traditional radio waves. Advancements in materials science have led to the development of stronger, lighter, and more heat-resistant materials. These materials are crucial for building spacecraft that can withstand the harsh conditions of space travel and planetary atmospheres. The integration of virtual reality, VR, and augmented reality, AR technologies in mission planning and astronaut training has enhanced the preparation for complex missions. These technologies provide immersive simulations of space environments and mission scenarios. Advances in life support systems are critical for long-duration human missions. Closed-loop systems that recycle air, water, and waste are essential for sustaining astronauts on missions to Mars and beyond. The development of reusable launch systems pioneered by companies like SpaceX has dramatically reduced the cost of access to space. Reusable rockets can be launched, landed, and relaunched multiple times, making space exploration more economically viable. Artificial intelligence and machine learning are being used to analyze vast amounts of data collected from space missions. These technologies can identify patterns and anomalies, leading to new discoveries and more efficient mission operations. Advances in satellite technology have enabled the deployment of small, cost-effective satellites known as CubeSats. These satellites can be used for a variety of purposes, including Earth observation, communications, and scientific research. The development of human-rated spacecraft, such as NASA's Orion and SpaceX's Crew Dragon, is paving the way for the next era of human space exploration. These spacecraft are designed to carry astronauts to the Moon, Mars, and potentially beyond. Technological advancements are also enhancing planetary protection measures. New sterilization techniques ensure that spacecraft do not contaminate other worlds, preserving their environments for scientific study. The continued evolution of space exploration technology promises to unlock new frontiers and deepen our understanding of the universe. These advancements not only make missions more feasible and cost-effective, but also expand the possibilities for scientific discovery and human exploration. The search for extraterrestrial life is one of the most exciting and profound quests in science. It seeks to answer the age-old question of whether we are alone in the universe. This search takes many forms, from studying extreme environments on Earth where life thrives, to exploring the surfaces and atmospheres of other planets and moons. Mars has been a prime target in the search for life due to evidence of past water. Rovers like Curiosity and Perseverance are exploring the Martian surface, looking for signs of ancient microbial life and habitable conditions. Jupiter's moon Europa is another key focus. Beneath its icy crust lies a subsurface ocean that may harbor life. Future missions, such as NASA's Europa Clipper, aim to investigate this potential. Saturn's moon Enceladus has geysers that spew water and organic molecules into space, indicating the presence of a subsurface ocean. The Cassini mission provided compelling evidence, and future missions could further explore its habitability. Triton, Saturn's largest moon, has lakes and rivers of liquid methane and ethane. Its unique chemistry and thick atmosphere make it an intriguing candidate for studying prebiotic chemistry and potential life. Exoplanets, planets orbiting stars outside our solar system, are also central to the search for life. The Kepler and TESS missions have discovered thousands of exoplanets, some of which are in the habitable zone where conditions might be right for life. The James Webb Space Telescope will soon provide detailed observations of exoplanet atmospheres, looking for signs of habitability and potential biosignatures like oxygen, methane, and other organic molecules. The study of extremophiles on Earth organisms that live in extreme conditions, help scientists understand the potential for life in harsh environments elsewhere. These organisms thrive in places like deep ocean vents, acidic hot springs, and the frozen tundra. Astrobiology, the study of life in the universe, combines biology, chemistry, geology, and astronomy to understand the potential for life beyond Earth. It seeks to uncover the origins, evolution, and distribution of life. Radio telescopes are used to search for signals from intelligent civilizations. Projects like SETI, the search for extraterrestrial intelligence, scan the skies for artificial radio signals that could indicate the presence of advanced extraterrestrial technology. The discovery of microbial life elsewhere in the solar system or beyond would have profound implications for our understanding of biology and the uniqueness of life on Earth. Even finding simple organic molecules on other planets or moons would be a significant step in understanding the building blocks of life and how common they might be in the universe. The search for extraterrestrial life also has cultural and philosophical implications. It challenges our perspectives on life, our place in the cosmos, and the possibility of civilizations far older and more advanced than our own. As technology advances and our exploration efforts expand, the search for extraterrestrial life will continue to be at the forefront of scientific discovery. It is a journey that promises to transform our understanding of the universe and our place within it. Human colonization of other celestial bodies is a bold and ambitious goal, with the Moon and Mars being the primary targets. The Moon, due to its proximity, is the logical first step. NASA's Artemis program aims to return humans to the Moon by 2024 and establish a sustainable presence by the end of the decade. This program will use the Lunar Gateway, an orbiting station around the Moon, as a staging point for missions. Living on the Moon will require developing habitats that can protect astronauts from harsh conditions, such as extreme temperatures, radiation, and micrometeorite impacts. These habitats will likely be built using lunar materials and advanced construction techniques like 3D printing. Lunar resources such as water ice at the poles could be used to produce oxygen, drinking water, and rocket fuel. This would reduce the need to transport supplies from Earth and make long-term habitation more feasible. The Moon will serve as a testing ground for the technologies and strategies needed for Mars colonization. Lessons learned from lunar missions will help refine the systems required for the longer, more challenging journey to Mars. Mars is the ultimate goal for human colonization due to its similarities to Earth, such as its day length and the presence of polar ice caps. However, Mars presents significant challenges, including its thin atmosphere, extreme cold, and radiation. NASA's Mars 2020 mission with the Perseverance rover is laying the groundwork for human missions by searching for signs of past life and testing technologies like the MOXIE experiment, which generates oxygen from Martian CO2. SpaceX is a key player in Mars colonization plans with its Starship spacecraft designed for deep space travel. SpaceX envisions a fleet of starships transporting people and cargo to Mars with the goal of establishing a self-sustaining colony. Living on Mars will require habitats that can provide protection from radiation and extreme temperatures. These habitats might be built underground or using Martian materials to create sturdy structures. In situ resource utilization, ISRU, is critical for Mars colonization. This involves using Martian resources such as water ice to produce essentials like air, water, and fuel. ISRU will reduce dependence on Earth and support long-term human presence. Agriculture on Mars will be essential for sustaining human life. Scientists are developing methods to grow food in Martian soil and controlled environments. ensuring a steady food supply for colonists. Transportation between Earth and Mars will involve long-duration space flights, taking about 6 to 9 months each way. Developing reliable life support systems and countermeasures for the effects of microgravity on the human body is crucial. International collaboration will likely play a significant role in colonizing Mars. Sharing resources, expertise, and funding will help overcome the immense challenges and ensure the success of human missions. The psychological and social aspects of living on another planet are also important considerations. Future colonists will need to adapt to isolation, confinement, and the challenges of living in a harsh and unfamiliar environment. The successful colonization of the Moon and Mars will represent a monumental achievement for humanity. It will expand our presence in the solar system, provide new opportunities for scientific discovery, and inspire future generations to reach for the stars. International collaboration has been a cornerstone of space exploration, enabling countries to pool resources, expertise, and technology to achieve shared goals. The International Space Station, ISS, is a prime example, with contributions from NASA, Roscosmos, ESA, JAXA, and CSA. The ISS serves as a hub for scientific research, technological development, and international cooperation. It has hosted astronauts from 19 different countries, fostering a spirit of collaboration and unity. Collaboration allows countries to undertake more ambitious missions than they could alone. By sharing costs and responsibilities, international partnerships can explore deeper into space and conduct more complex scientific experiments. The European Space Agency, ESA, and NASA have partnered on numerous missions, including the Hubble Space Telescope and the upcoming James Webb Space Telescope. These collaborations have expanded our understanding of the universe and pushed the boundaries of space science. Russia's Soyuz program has been vital in maintaining human presence in space, especially during the gaps in NASA's crewed launch capabilities. The mutual reliance on each other's technology has strengthened international bonds. Joint missions like the ExoMars program between ESA and Roscosmos aim to search for signs of life on Mars. These missions benefit from the combined expertise and technology of both space agencies, enhancing the scientific return. The Lunar Gateway project is another example of international collaboration involving NASA, ESA, JAXA, and CSA. This lunar outpost will support missions to the Moon and beyond, showcasing how collaboration can extend human presence in space. International collaboration is also crucial for addressing global challenges, such as space debris. Working together, countries can develop and implement strategies to mitigate the risks posed by increasing amounts of debris in orbit. Space exploration fosters diplomatic relations and peace. By working together on common goals, countries build trust and understanding, which can extend beyond space to other areas of international relations. The sharing of data and scientific findings accelerates progress. When countries share their discoveries, the global scientific community can build on this knowledge, leading to faster advancements and new breakthroughs. Emerging space nations benefit from international partnerships by gaining access to technology and expertise. This support helps them develop their own space programs and contribute to global space exploration efforts. Public engagement and inspiration are amplified through international missions. Collaborative projects capture the imagination of people worldwide, demonstrating what humanity can achieve when we work together. International space organizations, such as the United Nations Office for Outer Space Affairs, UNOSA, play a crucial role in coordinating efforts and establishing guidelines for peaceful and cooperative use of space. Future missions to Mars and beyond will likely require unprecedented levels of international collaboration. The technical and financial challenges are immense, and pooling global resources will be essential for success. The future of space exploration depends on our ability to work together as a global community. By continuing to collaborate, we can overcome the challenges of space and unlock the mysteries of the universe for the benefit of all humanity. Throughout this comprehensive guide to the solar system, we've journeyed from the heart of our sun to the distant reaches of the Kuiper Belt, exploring the vast array of celestial bodies that make up our cosmic neighborhood. We began by understanding the sun's composition and energy production, crucial to sustaining life on Earth and driving the dynamic processes within the solar system. Our exploration took us to Mercury with its extreme temperatures and magnetic field, and Venus with its thick, toxic atmosphere and volcanic landscape. We delved into the fascinating details of Earth's unique characteristics, from its geological features and climate systems to the intricate web of life that thrives on its surface. Mars captivated us with its potential for past water and the exciting prospects for future human colonization. Jupiter's immense size, powerful storms, and intriguing moons revealed the complexity of the gas giant, while Saturn's iconic rings and diverse moons showcased the beauty and mystery of our planetary system. The outer planets, Uranus and Neptune, offered insights into the dynamics of ice giants with their unique tilts, extreme weather patterns, and rich atmospheres. The discovery and study of dwarf planets like Pluto, Eris, Haumea, and Makemake highlighted the diversity of objects in the Kuiper Belt and the ongoing quest to understand their origins and evolution. We also explored the technological advancements and international collaborations that drive space exploration, enabling us to push the boundaries of what is possible. The search for extraterrestrial life and the potential for human colonization of the Moon and Mars represent the next frontiers in our quest to explore and understand the cosmos. As we look to the future, upcoming missions and projects promise to expand our knowledge even further, offering new opportunities for discovery and exploration. The role of international collaboration will be crucial in these endeavors, ensuring that we can achieve our shared goals and unlock the mysteries of the universe. If you enjoyed this deep dive into the solar system and want to continue exploring the wonders of space, please like this video and subscribe to our channel. Don't forget to check out our other videos where we cover a wide range of topics from the latest space missions to the most intriguing astronomical phenomena. Thank you for joining us on this cosmic journey, and we look forward to bringing you more exciting content in the future.